Welcome to Sleepy Stories, a place where you can rest while learning about the natural world. Each episode is designed to move slowly, with clear explanations and calm pacing, so your mind can relax while curiosity stays awake. There is no need to concentrate hard or to remember details. Simply listen, let the words pass through, and allow understanding to arrive on its own. If sleep doesn't come immediately, that's perfectly normal. Just stay comfortable and let the sound of information become part of the quiet. And if these peaceful nights help you, a simple like or subscribe helps us continue creating stories that bring calm and knowledge together. Tonight, we begin with the ground itself, the surface that supports everything you see. It feels firm and unchanging, but that impression is only an illusion created by the speed of human life. The earth is constantly moving, adjusting, and renewing itself. Even now, while you are lying still, the crust beneath you shifts by a few millimeters each year. Continents drift, oceans widen, and mountains slowly rise. The processes are so gradual that we rarely notice them, yet they shape every landscape we know. The Earth's interior is built in layers. At the center lies the core, extremely hot and dense, made mostly of iron and nickel. Around it is the mantle, a vast zone of solid rock that behaves like a very slow fluid over long periods of time. Heat from the core causes parts of the mantle to move upward, while cooler material sinks downward, forming circular currents called convection cells. These currents act like conveyor belts that push and pull the outer crust, breaking it into large, rigid pieces known as tectonic plates. The crust itself is surprisingly thin compared to the size of the planet, about 30 kilometers thick under continents and less than 10 beneath oceans. To scale, it would be thinner than the shell of an egg. Yet this fragile layer holds all of life, air and water. It is divided into plates that meet along enormous boundaries stretching thousands of kilometers. At these boundaries, energy accumulates as the plates press, scrape, or separate. Most earthquakes originate there, where that stored energy is finally released. What we call an earthquake is not an explosion but a rapid movement along one of these faults. When stress exceeds the strength of the rock, it slips, sending waves through the surrounding material. Those waves spread outward, shaking everything above them. Each event is a mechanical process governed by friction, pressure, and elasticity. The ground moves, then returns to rest. From a geological perspective, this is completely normal. It is one of the ways the planet maintains balance between built-up forces. The energy involved is immense, but it does not mean the planet is unstable. On the contrary, these adjustments allow it to remain structurally sound over billions of years. Without the constant release of tension, the crust would lock and crack more violently. Earthquakes are therefore part of the system that keeps the planet dynamic yet intact, a safety valve in the circulation of heat and motion from the core to the surface. In this series, we will look closely at how that system works. You will learn how scientists measure ground motion with seismographs, how energy is quantified using magnitude scales, and how modern technology helps us understand what lies deep beneath the crust. We will discuss the great fault zones, such as the Pacific's Ring of Fire, and explore how earthquakes have shaped mountains, oceans, and human civilization. Each part will focus on clarity and calm explanation rather than drama, allowing you to follow the story without tension. As you listen, you can think of the Earth not as fragile, but as remarkably self-regulating. Its interior heat drives cycles that have operated since the planet formed. Rock melts and solidifies, continents split and rejoin, oceans open and close. The crust may shake, but the world remains whole. Every movement you will hear about tonight belongs to that long pattern of transformation that makes Earth a living planet rather than a static one. So, as you settle into rest, know that you are lying on a surface that is both stable and alive. The same slow forces that once raised mountains and carved valleys continue their work beneath you right now, steady, quiet, and almost unimaginably patient. And as the story unfolds, you can let that knowledge bring comfort. Even in motion, the planet maintains its balance. Beneath everything we know, the oceans, the forests, the cities, lies a surprisingly thin layer of rock called the crust. It feels solid and endless when we walk across continents, yet compared to the size of the planet, it is almost fragile. If the Earth were reduced to the size of an apple, the crust would be no thicker than the skin. It is this delicate surface that carries all living things, separating the cool air above from the deep heat below. The crust exists in two main forms: continental and oceanic. Continental crust makes up the dry land and the shallow seabeds around it. It is thick, averaging about 30 kilometers, and made mostly of light, silica-rich rocks such as granite. Oceanic crust, which underlies the deep sea, is thinner, only about 7 kilometers on average, and composed of darker, denser basalt. Because of this difference in composition and weight, the ocean floors sit lower, allowing water to collect and form the vast basins that define our planet's blue face. Although it seems motionless, the crust is not fixed in place. It is divided into several large tectonic plates that move slowly over the upper mantle. These plates fit together like an imperfect mosaic, their edges pressing, sliding, or pulling apart. Every continent and ocean basin is part of one of these plates, which shift a few centimeters per year. Over millions of years, this steady drift rearranges the continents, builds new mountains, and opens new seas. The material of the crust is mostly solid rock, but its properties vary with depth. Near the surface, weathering and erosion break rock into soil, creating the layer that supports life. Deeper down, pressure and temperature increase, and minerals lock tightly together. The lower boundary of the crust merges gradually into the mantle through a zone called the Mohorovičić discontinuity, or simply the MOHO. It marks a change in density and seismic speed rather than a visible line. When seismic waves travel through the Earth, they speed up sharply at this boundary, revealing its presence even though we can't reach it directly. Within the crust, stress is always present. Thermal expansion, gravitational forces, and the constant tug of moving plates create slow but persistent tension. Rock resists deformation for long periods, but under sustained stress it bends or fractures. Over time, these fractures can connect into faults, natural breaks where motion can occur. The crust, though solid, behaves like an elastic shell that occasionally relieves pressure through small adjustments or larger ruptures. The crust also records its own history. Each layer of rock tells a story of formation, volcanic eruptions, sedimentation in ancient seas, and the folding and metamorphosis of material under great heat and pressure. By studying these layers, geologists reconstruct the planet's past climates and the movement of its plates. Fossils trapped in sedimentary rock mark intervals of stability between upheavals. In this way, the crust serves as both foundation and archive. Human life depends completely on the stability of this outer layer, yet our perspective is limited to the brief moments in which it remains calm. Most of the time, the forces acting within the crust are invisible. A farmer ploughing a field or a builder laying a foundation rarely thinks about the immense structure beneath. But under every field and city, rock layers shift imperceptibly, adjusting to pressure from below and from their neighbors. The crust's role in regulating surface conditions is essential. It acts as a lid that keeps the planet's internal heat from escaping too quickly, while still allowing gradual release through volcanoes and hydrothermal vents. It provides minerals that feed ecosystems and the chemical balance that sustains oceans and air. Without this thin, dynamic layer, Earth could not support liquid water or a stable climate. When viewed with patience, the crust is not a static floor but a moving boundary between two worlds, the cool atmosphere and the fiery interior. It carries the evidence of ancient collisions and quiet separations, of long ages when continents gathered and drifted apart. Every grain of sand and every mountain peak began as part of this shifting surface. To understand earthquakes, we must first understand the crust itself, delicate, durable, and always in motion beneath the appearance of stillness. Beneath everything we know, the oceans, the forests, the cities, lies a surprisingly thin layer of rock called the crust. It feels solid and endless when we walk across continents, yet compared to the size of the planet, it is almost fragile. If the Earth were reduced to the size of an apple, the crust would be no thicker than the skin. It is this delicate surface that carries all living things, separating the cool air above from the deep heat below. The crust exists in two main forms, continental and oceanic. Continental crust makes up the dry land and the shallow seabeds around it. It is thick, averaging about 30 kilometers, and made mostly of light, silica-rich rocks such as granite. Oceanic crust, which underlies the deep sea, is thinner, only about 7 kilometers on average, and composed of darker, denser basalt. Because of this difference in composition and weight, the ocean floors sit lower, allowing water to collect and form the vast basins that define our planet's blue face. Although it seems motionless, the crust is not fixed in place. It is divided into several large tectonic plates that move slowly over the upper mantle. These plates fit together like an imperfect mosaic, their edges pressing, sliding, or pulling apart. Every continent and ocean basin is part of one of these plates, which shift a few centimeters per year. Over millions of years, this steady drift rearranges the continents, builds new mountains, and opens new seas. The material of the crust is mostly solid rock, but its properties vary with depth. Near the surface, weathering and erosion break rock into soil, creating the layer that supports life. Deeper down, pressure and temperature increase, and minerals lock tightly together. The lower boundary of the crust merges gradually into the mantle through a zone called the Mohorovičić discontinuity, or simply the MOHO. It marks a change in density and seismic speed rather than a visible line. When seismic waves travel through the Earth, they speed up sharply at this boundary, revealing its presence even though we can't reach it directly. Within the crust, stress is always present. Thermal expansion, gravitational forces, and the constant tug of moving plates create slow but persistent tension. Rock resists deformation for long periods, but under sustained stress it bends or fractures. Over time, these fractures can connect into faults, natural breaks where motion can occur. The crust, though solid, behaves like an elastic shell that occasionally relieves pressure through small adjustments or larger ruptures. The crust also records its own history. Each layer of rock tells a story of formation, volcanic eruptions, sedimentation in ancient seas, and the folding and metamorphosis of material under great heat and pressure. By studying these layers, geologists reconstruct the planet's past climates and the movement of its plates. Fossils, trapped in sedimentary rock, mark intervals of stability between upheavals. In this way, the crust serves as both foundation and archive. Human life depends completely on the stability of this outer layer, yet our perspective is limited to the brief moments in which it remains calm. Most of the time, the forces acting within the crust are invisible. A farmer ploughing a field or a builder laying a foundation rarely thinks about the immense structure beneath. But under every field and city, rock layers shift imperceptibly, adjusting to pressure from below and from their neighbors. The crust's role in regulating surface conditions is essential. It acts as a lid that keeps the planet's internal heat from escaping too quickly, while still allowing gradual release through volcanoes and hydrothermal vents. It provides minerals that feed ecosystems and the chemical balance that sustains oceans and air. Without this thin, dynamic layer, Earth could not support liquid water or a stable climate. When viewed with patience, the crust is not a static floor but a moving boundary between two worlds, the cool atmosphere and the fiery interior. It carries the evidence of ancient collisions and quiet separations, of long ages when continents gathered and drifted apart. Every grain of sand and every mountain peak began as part of this shifting surface. To understand earthquakes, we must first understand the crust itself, delicate, durable, and always in motion beneath the appearance of stillness. The surface of our planet is never truly still. The continents and ocean floors that seem fixed in place are pieces of a global structure of tectonic plates, large slabs of rigid rock that float on the softer layer of the upper mantle. Although we do not feel it, these plates are constantly moving. Their motion is slow, steady, and guided by the internal heat of the Earth. Over long periods, this movement shapes every landscape we know. Scientists first suspected this planetary motion in the early 20th century when they noticed that the coastlines of continents fit together like puzzle pieces. Similar fossils and rock formations were found on lands now separated by oceans. These clues suggested that continents had once been joined. Later discoveries confirmed that the ocean floor itself was spreading apart, producing new crust at mid-ocean ridges, while older crust disappeared into deep trenches elsewhere. The theory of plate tectonics brought all these observations together, revealing a single dynamic system operating beneath our feet. The driving force behind this motion is convection in the mantle. Heat from the core warms material at the base of the mantle, making it less dense, so it slowly rises. As it reaches cooler regions, it spreads outward, cools, and sinks again. These slow circular currents exert gentle drag on the overlying plates, setting them in motion. Where convection cells rise, plates move apart and magma fills the gap, creating new crust. Where they sink, plates converge and one is forced beneath another, returning material to the deep interior. There are about a dozen major plates and several smaller ones. Among them are the Pacific, Eurasian, African, North American, South American, and Antarctic plates. Each moves at its own speed, usually between 2 and 10 centimeters per year. Though this seems tiny, it adds up to thousands of kilometers over geological time. The world we inhabit today, with its arrangement of continents and oceans, is simply one temporary configuration in a long sequence of shifting patterns. When plates move apart, new seafloor is born. At mid-ocean ridges, molten rock rises from below, cools, and hardens into basalt. This process continuously renews the oceanic crust. When plates collide, mountain ranges form as rock is compressed and uplifted. The Himalayas, for example, exist because two continental plates continue to push against each other, forcing the land upward. Where plates slide past each other, as along California's San Andreas Fault, the motion is sideways, generating frequent but often moderate earthquakes. The interactions between plates control many of the Earth's surface features. Volcanoes, ocean trenches, island arcs, and earthquake zones all trace the boundaries where plates meet. Even regions far from these boundaries feel the effects over time, as stresses migrate through the crust. This constant rearrangement explains why ancient coral reefs can be found high in mountain rock, and why coal beds occur in places that are now cold and dry. Understanding plate motion has also deepened our sense of time. Human lifetimes are too short to notice continents drifting, but geological records reveal the evidence clearly. Rocks formed on the ocean floor capture the direction of Earth's magnetic field at the time of their creation. As new crust forms and spreads, alternating magnetic patterns appear on either side of ridges, recording millions of years of slow but continuous movement. These symmetrical stripes provide direct proof that the surface of the planet expands and contracts in cycles. Despite the vastness of this process, its mechanics are simple. Heat moves upward, rock circulates, and the crust responds. The system operates with efficiency and patience. When the forces reach a boundary, stress accumulates. When it is released, the ground trembles. Earthquakes are one result of this steady internal energy, a reminder that the planet is not a static sphere but a dynamic engine of change. As we continue our exploration, we will look more closely at those boundaries where plates meet and where energy concentrates. There, the calm motion of deep time becomes visible, and the invisible movement of the Earth occasionally touches the surface we call home. Where tectonic plates meet, the Earth's quiet motion becomes visible. Along these boundaries, the planet releases energy, builds mountains, and reshapes oceans. Scientists classify three main types of boundaries: divergent, convergent, and transform. Each behaves differently, yet all are expressions of the same system driven by internal heat. Understanding them explains where most earthquakes occur and why some regions of the world feel the ground move more often than others. At divergent boundaries, plates move apart. In the oceans, this creates long ridges, chains of volcanic mountains running through deep water. Molten material rises from the mantle to fill the gap, cools, and forms new crust. The Mid-Atlantic Ridge is one of the largest examples, a continuous seam that adds fresh rock to the ocean floor each day. Although spreading happens slowly, the constant creation of new crust pushes continents farther apart over millions of years. On land, similar rifting zones can form valleys and lakes, such as those seen in East Africa. These areas often experience small, frequent earthquakes, as the crust stretches and cracks to accommodate movement. At convergent boundaries, plates collide. When an oceanic plate meets a continental one, the heavier oceanic crust slides beneath the lighter continental crust in a process called subduction. As it sinks into the mantle, the descending slab melts and releases gases, producing chains of volcanoes at the surface. The Andes of South America and the volcanic arc of Japan exist because of such collisions. Where two continental plates converge, neither easily sinks, so the crust folds and thickens, creating high mountain ranges. The Himalayas continue to rise for this reason, even as erosion wears them down. These regions store enormous stress within the rock. When it is released, powerful earthquakes can result. Transform boundaries form where plates slide horizontally past each other. The most well-known example is the San Andreas Fault in California, a long fracture marking the junction between the Pacific and North American plates. Here the plates grind slowly, moving a few centimeters per year, but friction prevents smooth motion. Stress builds along the fault until it abruptly slips, sending shock waves across the landscape. Because transform motion neither creates nor destroys crust, these boundaries act more like seams that allow the planet's shell to adjust without changing its overall size. The behavior of these boundaries demonstrates the balance between movement and resistance inside the Earth. Rock is strong, but not infinitely strong. It bends under pressure, then breaks when its limit is reached. The stored energy is released as seismic waves that travel outward through the crust. In most cases, the amount of energy is small, and the shaking goes unnoticed. Only when large segments of a fault rupture at once do we feel the ground move beneath us. Even then, the event lasts only seconds, while the preparation for it may have taken centuries. Scientists map plate boundaries using satellite measurements, seismic data, and ocean floor studies. Global networks of instruments now track their motion with remarkable precision. By combining this information with models of stress accumulation, researchers can identify regions most likely to experience major earthquakes. While exact prediction remains impossible, such knowledge helps engineers design safer buildings and planners prepare communities for risk. The boundaries, once symbols of destruction, have become laboratories for understanding stability. Despite their differences, all three types of boundaries serve a single function. They let the planet recycle its outer layer. New crust forms at divergent ridges, old crust sinks at subduction zones, and horizontal faults maintain the balance between them. Through these processes, the Earth renews itself continuously, preserving a balance between creation and decay. When you think of these boundaries, imagine not sharp lines but vast zones of gradual transition. Even in apparent rigidity, the crust behaves as part of a flexible system. What we call solid ground is, in reality, part of a global mechanism that keeps heat flowing and material circulating. The next time you stand on stable soil, it might help to remember that this stability is the outcome of motion, millions of years of adjustment between plates that meet, separate, and meet again. A fault line begins as a simple fracture in rock, a small crack produced by stress that has built up over time. At first, the break may be microscopic, invisible even under close inspection, but as stress continues to act, those small imperfections connect. Over thousands of years, the joined cracks create a plane of weakness that can stretch for hundreds of kilometers. Along this plane, sections of the crust move relative to each other, forming what scientists call a fault. Every major earthquake in history has occurred on one of these hidden surfaces. The development of a fault depends on three factors: stress, strength, and time. Stress is the force applied to the rock, caused by the movement of tectonic plates, by the weight of mountains, or by changes in temperature and pressure. Strength is the rock's ability to resist that force. When stress exceeds strength, deformation occurs. If the material bends, we see folds. If it breaks, a fault is born. Time governs both, because the longer stress is applied, the more likely the rock is to yield. Faults can form in several ways. Normal faults appear where the crust is being stretched. One block of rock slides downward relative to the other, creating valleys or basins. Reverse faults occur where the crust is compressed, forcing one block up and over another, building ridges and mountain fronts. Strike-slip faults form where motion is horizontal, as one side moves past the other. The San Andreas system in California and the North Anatolian Fault in Turkey are well-known examples. Each type reflects a different kind of stress, but all result from the same fundamental process: the crust adjusting to forces too large to ignore. The friction along a fault surface is what allows energy to accumulate. As plates move, the sides of the fault catch on irregularities, holding tight even though the deeper forces continue to push. Elastic strain builds until the stress surpasses the frictional strength, and the fault suddenly slips. The movement releases energy in the form of seismic waves that radiate through the ground. The amount of slip can be a few centimeters or several meters, depending on the size of the rupture and the amount of stored stress. After the slip, the fault locks again, and the cycle of strain begins anew. Geologists study faults to understand this cycle. They map visible scarps on the surface, analyze displaced rock layers, and use satellite radar to detect subtle movements invisible to the eye. In deep boreholes, instruments measure temperature, stress, and fluid pressure, revealing how conditions change before and after a quake. Laboratory experiments replicate fault behavior using rock samples under controlled stress, helping researchers determine how friction, mineral composition, and pore fluids influence the moment of failure. Together, these methods build a picture of how faults grow and behave over time. Not all faults reach the surface. Many remain buried beneath layers of sediment, known only through seismic imaging. These blind faults can produce damaging earthquakes without visible warning because their motion is concealed. Others, long inactive, mark ancient plate boundaries where stress has shifted elsewhere. Even when quiet, a fault remains a structural weakness, an imprint of the planet's continuous effort to release tension. Fault formation is not instantaneous. It is a gradual response to persistent pressure. What seems like a sudden event is the visible end of a long, invisible process. Rock behaves elastically for centuries before it fractures, accumulating potential energy with immense patience. When the release finally occurs, the stored motion becomes vibration. The ground moves, and the crust finds a new position of balance. To imagine a fault is to picture a vast interface between two worlds of rock, each pushing, pulling, or sliding against the other. Along that narrow zone, the story of an earthquake begins. Energy gathers, resistance holds, and at some future moment, the balance will tip. Faults are not scars of weakness, but records of adjustment, lines that mark where the planet has learned to move rather than break apart entirely. For long periods, the rocks beneath us hold tension without complaint. At plate boundaries and within faults, pressure grows slowly as sections of the crust resist movement. The stored energy remains locked, invisible, and silent, until it reaches a point where friction can no longer keep the rocks in place. In that instant, the fault slips. The movement may span only a few meters, but the energy released spreads across thousands of kilometers. This is the moment of an earthquake. During an earthquake, the fault rupture begins at a single point called the focus or hypocenter. It lies somewhere beneath the surface, often many kilometers deep. From there, the rupture spreads along the fault in both directions, breaking rock as it goes. The point on the surface directly above the focus is known as the epicenter, the location where shaking is often felt most strongly. As the fault slips, stored strain energy is converted into seismic waves, vibrations that travel through the crust and mantle. The process happens with remarkable speed. Rupture fronts can move at several kilometers per second, and within seconds, the waves reach the surface. These vibrations make the ground move up and down, side to side, or in circular rolling patterns. Depending on the depth, rock type, and geometry of the fault, some earthquakes produce short, sharp jolts, while others create long, swaying motions. Each event is a complex physical response to stress redistribution within the planet's outer shell. The energy involved can be enormous. Even a moderate earthquake releases more power than the largest man-made explosion. In a major event, the amount of energy liberated equals that produced by thousands of nuclear tests. Yet most of this energy does not appear as destruction. It spreads through the earth as waves, dissipating gradually, and a large fraction is absorbed or converted to heat. Only a small portion affects the surface strongly enough to cause damage. The rest continues its journey through the planet, where instruments record it as data. After the rupture, the fault does not stay open. Friction and gravity cause the blocks of rock to settle again, finding a new position of balance. The stress that was concentrated in one place redistributes itself along the fault and surrounding crust. This redistribution often triggers smaller movements known as aftershocks. They are not separate earthquakes in the full sense, but adjustments that help the crust reach stability after its sudden release. The moment of an earthquake is short, but its preparation takes centuries. In that sense, each event is the final step in a long natural cycle. Rock bends, accumulates strain, and finally breaks when its strength limit is reached. Once the energy is released, the cycle starts again. Understanding this pattern helps scientists view earthquakes not as isolated incidents but as part of a continuous process of planetary renewal. Without these periodic releases, the planet's crust would lock under mounting pressure until far more catastrophic ruptures occurred. For scientists, studying this moment of release provides essential information about the structure of the Earth. By analyzing the arrival times of seismic waves at different monitoring stations, they can calculate the location, depth, and size of an earthquake. These measurements reveal not only the properties of the fault but also the composition of the materials the waves have traveled through. Each event, no matter how small, becomes a probe into the planet's hidden interior. While earthquakes can be destructive, they also serve a stabilizing function. They redistribute energy, reshape landscapes, and create space for new geological formations. The same forces that cause shaking also uplift mountains, form basins, and expose minerals vital for life. In that sense, the planet's restlessness is a form of balance, motion that maintains structure through constant adjustment. As you listen and perhaps prepare to rest, it can be comforting to remember that even the Earth, vast as it is, needs its moments of release. Beneath the surface, tension builds slowly, and then resolves in motion, followed by calm. In your own body, tension and rest follow a similar rhythm. Muscles tighten, then relax, thoughts gather, then settle. The planet and the person share the same pattern of balance through release. If you notice your breath slowing, you are echoing the same principle that keeps the Earth whole. After every quake, the ground eventually steadies, and quiet returns. That quiet is not emptiness but recovery. The planet restores its equilibrium, just as we do after strain. The energy of motion fades into stillness, and the cycle begins again, patient, inevitable, and endlessly balanced. When the ground shakes, what we feel is the passage of seismic waves, vibrations that travel outward from the source of an earthquake through the body of the Earth. These waves are similar in principle to sound waves moving through air, but instead of compressing and expanding gas, they distort solid rock. Understanding how these waves move and interact allows scientists to locate earthquakes, determine their strength, and even map the planet's internal layers. There are two broad types of seismic waves: body waves, which travel through the interior of the Earth, and surface waves, which move along the crust. Body waves come in two main forms: primary, P waves, and secondary, S waves. P waves are compressional waves. As they move through rock, particles are pushed forward and pulled back in the same direction as the wave travels. These are the fastest seismic waves, arriving first at detection stations. S waves are shear waves, moving rock particles perpendicular to the wave's direction, side to side, or up and down. They travel more slowly and cannot move through liquid, which is why they stop at the outer core. By measuring the time difference between the arrival of P waves and S waves, seismologists can estimate how far away an earthquake occurred. The greater the gap in arrival times, the farther the source. Using data from multiple stations, scientists can pinpoint the exact location of the earthquake's focus. This method was one of the first ways humans learned to see inside the Earth without direct observation. At the surface, waves become more complex. Surface waves travel along the top few kilometers of the crust and usually cause the most visible shaking. Two types dominate: love waves and Rayleigh waves. Love waves move the ground horizontally, like a snake undulating along the surface, while Rayleigh waves create a rolling motion similar to waves on the ocean. These motions combine to shake buildings and infrastructure, especially where the soil amplifies the vibrations. The interaction of different wave types explains why each earthquake feels distinct, with some producing sharp jolts and others long, smooth sways. Seismic waves behave differently depending on the materials they encounter. They speed up through dense, solid rock and slow down through softer sediments. They also bend, or refract, when moving between layers of different density. This behavior allows scientists to use them much like medical imaging tools. By analyzing how waves curve, reflect, or disappear, researchers can infer the composition of layers deep below the surface. It is through this technique that we know the core of the Earth is liquid iron, surrounded by a solid inner core. The amplitude, or height, of the waves determines how much the ground moves. Energy spreads out as waves travel, so the shaking weakens with distance. However, local conditions, such as the type of soil or the geometry of nearby valleys, can concentrate or extend the motion. This is why two towns at the same distance from an epicenter may experience very different levels of shaking. Engineers use this knowledge to design structures that can withstand specific wave types and frequencies, reducing damage during major events. Seismographs capture these vibrations with remarkable sensitivity. Modern instruments use electronic sensors that detect motion thousands of times smaller than what a human can feel. The signals they record appear as waveforms on a computer, showing the arrival times and amplitudes of P, S, and surface waves. When combined globally, this network of instruments allows continuous monitoring of the entire planet. A large earthquake anywhere in the world produces signals that circle the globe several times before fading. Beyond earthquake detection, seismic waves have revealed much about the planet's structure. Variations in travel time indicate transitions between layers of differing density and composition. The study of these variations led to the identification of the mantle, outer core, and inner core, each with distinct physical properties. Every quake, therefore, contributes to a growing picture of the Earth's anatomy, expanding our understanding of a world we can never directly enter. Although the science of seismic waves is highly technical, the principle behind it is simple. Energy seeks balance. When the crust moves, that energy must travel somewhere, and it moves as waves through rock, air, and water until it disperses. The shaking we feel is only the surface expression of that journey. It is motion transformed into vibration, vibration into information, and information into understanding, a chain that connects human observation with the invisible heart of the Earth. The first people to study earthquakes scientifically faced a fundamental challenge. The events they wanted to observe were unpredictable and invisible. The ground shook for only a short time, and by the moment observers arrived, the motion was gone. What remained were cracks, fallen stones, and confused memories of movement. To study something so brief and elusive, scientists needed a way to measure the Earth's motion directly and record it without human reaction or interpretation. That challenge led to one of the most important instruments in geophysics, the seismograph. A seismograph works on a simple principle of inertia. When the ground moves, a suspended mass tends to remain still. If that mass is connected to a pen or sensor, the relative motion between the mass and the moving frame can be traced or recorded. Early devices used mechanical parts, a heavy weight hanging from a frame that shifted with the ground, marking its movement on a rotating drum of paper. As the ground shook, the pen drew a wavy line known as a seismogram. Each curve represented motion through time. The amplitude showed the strength of the shaking, and the spacing between waves revealed its frequency and duration. The invention of such instruments in the 19th century transformed seismology from speculation into measurable science. For the first time, researchers could compare earthquakes in different regions and see patterns that were invisible to the naked eye. They learned that ground motion arrived in distinct phases: the fast P waves, followed by slower S waves, then surface waves. These recorded signatures made it possible to calculate distances and identify where earthquakes began. Every new seismograph added another ear to a growing global network, allowing humanity to listen to the planet in ways that had never been possible before. Modern seismographs are far more sensitive than their early mechanical ancestors. Instead of pens and paper, they use electronic sensors and digital processors. The basic principle, however, remains the same. A stable mass is isolated from ground motion as much as possible, while detectors measure its relative movement. These instruments can detect vibrations smaller than a micrometer, motions so slight they would be imperceptible to humans or even to most structures. Data from multiple instruments are transmitted in real time to monitoring centers, where automated systems analyze them within seconds. The resulting network has turned the Earth into a kind of living laboratory. Thousands of stations around the world record continuous streams of data. When an earthquake occurs, scientists can triangulate its location and magnitude almost immediately. Even small tremors, unnoticed by people, appear clearly on global records. The entire planet vibrates at a low level all the time, and seismographs capture this background noise as well. These tiny signals come from waves hitting shorelines, wind interacting with the ground, or the steady hum of human activity. Together they form the planet's continuous soundtrack. Because seismic waves travel through every layer of the Earth, their paths carry information about what lies within. By studying how those waves speed up, slow down, or bend as they pass through different materials, researchers can infer the composition and temperature of regions deep below the surface. Seismology has therefore become not just a study of earthquakes, but a tool for imaging the entire planet. It provides data for geophysics, mineral exploration, and even climate research, as the movement of ice and water also generates detectable vibrations. One of the most useful developments has been the seismograph array, a group of sensors arranged across large distances to record waves simultaneously. Comparing their readings allows scientists to filter out noise and focus on true seismic signals. Networks like these detect not only natural earthquakes, but also other forms of ground motion, such as volcanic activity, landslides, and underground explosions. Governments and research institutions use them for both safety and science, combining their data into shared international catalogues. In a way, these instruments have given humanity a new sense, an ability to feel what the planet feels. The shaking that once seemed random now appears as patterns of energy following physical laws. Each seismogram is a direct record of motion, a fingerprint of stress and release that helps us understand the Earth's inner rhythm. By capturing what our bodies cannot perceive, seismographs have turned the invisible into something measurable and meaningful. The idea that our solid ground is in constant motion can be unsettling, yet the precision of modern measurement brings reassurance. What was once chaos now has structure. What was mystery now has data. Through instruments built with care and patience, we have learned to listen to the planet itself. And every line drawn by a seismograph, every rise and fall of the trace, is the Earth communicating in its own quiet, mechanical language. When people hear about an earthquake, the first question is often the same: how strong was it? To answer that question, scientists use magnitude, a measure of the energy released at the source of an earthquake. The best-known system for expressing this energy is the Richter scale, developed in the early 20th century, which gave seismology a universal language for describing what had once been only felt or guessed. Before standardized scales existed, reports of earthquakes were purely descriptive. One community might describe a quake as severe, another as moderate, and the comparison meant little across distances. The introduction of numerical measurement changed that. When Charles F. Richter and Benno Gutenberg analyzed seismograms from Southern California, they realized that the amplitude of the largest wave on a seismograph could be related mathematically to the earthquake's energy. This insight led to the Richter magnitude scale, which expressed strength as a single number, allowing scientists to compare earthquakes anywhere on Earth. The Richter scale is logarithmic, meaning that each whole number increase represents 10 times greater ground motion and roughly 30 times more energy release. A magnitude 6 earthquake, for example, releases about 30 times more energy than a magnitude 5 event. This exponential structure captures the vast range of possible earthquake sizes, from tremors so small that only instruments detect them to rare events capable of shifting landscapes. The scale also provides a framework for studying the frequency of earthquakes. Small ones happen constantly, moderate ones occasionally, and large ones rarely, following predictable statistical patterns. However, as technology advanced, scientists found that the original Richter formula worked best for moderate earthquakes recorded within a limited distance from their source. For very large or deep events, it underestimated the total energy released. To solve this, seismologists developed the moment magnitude scale, now the standard in global reporting. This newer system calculates the seismic moment, a value based on the area of the fault that slipped, the average movement along the fault, and the rigidity of the rocks involved. The result still appears as a number similar to a Richter magnitude, but it is physically grounded and consistent across all earthquake sizes. The moment magnitude scale ensures that magnitudes represent true energy release, not just the motion recorded at a specific location. Because it's logarithmic as well, the same principle applies. An increase of 1 unit corresponds to about 30 times more energy. This simplicity makes it easy for both scientists and the public to understand relative power without needing complex units. What the public calls the Richter scale today is technically this more accurate modern system. Magnitude differs from intensity, another common measure of earthquake impact. Magnitude describes the energy released at the source, while intensity reflects how strongly the shaking is felt at a specific location. Intensity depends on distance from the epicenter, local geology, and construction quality. The modified Mercalli intensity scale expresses these effects using Roman numerals, ranging from barely noticeable tremors to catastrophic destruction. Together, magnitude and intensity provide a full picture: how powerful the earthquake was, and how it affected people and structures on the surface. Accurate measurement of magnitude allows scientists to build long-term catalogues of earthquakes, identifying regional patterns and recurrence intervals. These records support risk assessments and safety planning. By studying the statistical relationships between magnitudes and their frequency, researchers can estimate the probability of future large events in active zones. While predictions to the exact day remain impossible, magnitude data make it possible to prepare communities for the range of motion they might one day face. Modern technology has improved both precision and speed. Digital seismographs automatically send data to analysis centers within seconds of detecting movement. Algorithms calculate preliminary magnitudes almost immediately, later refined as more data arrives. The results are shared globally, allowing agencies and researchers to coordinate rapid responses. Every new earthquake adds another data point to our understanding of how energy moves through the planet. Although a single number cannot capture the complexity of an earthquake, it provides a clear way to compare events separated by continents and centuries. Magnitude brings order to natural variation, transforming chaos into quantifiable structure. When you hear that an earthquake measured magnitude 7, it means that deep inside the Earth, a tremendous amount of stored energy was released, an energy that, though brief, becomes part of the ongoing balance of a living planet. In this sense, magnitude is more than a statistic. It is a measure of motion transformed into information, a symbol of how far science has come in translating the planet's language into human understanding. What was once frightening and unpredictable can now be expressed in calm, consistent terms, a reminder that even the Earth's most dramatic moments can be understood through careful observation and shared knowledge. To the human eye, earthquakes seem unpredictable and chaotic. They strike without warning, vary in strength, and leave behind patterns that appear random. Yet beneath that apparent disorder, scientists have discovered consistent laws that describe how and why they occur. These laws do not allow us to forecast the exact moment of an earthquake, but they reveal that the planet's motion follows order, not chance. One of the most important discoveries is the Gutenberg-Richter law, a mathematical relationship describing the frequency of earthquakes relative to their magnitude. It shows that small earthquakes are far more common than large ones, and that this ratio remains nearly constant worldwide. For every increase of 1 magnitude unit, the number of events decreases by roughly a factor of 10. This means that for each major quake, there are hundreds of moderate ones and thousands of minor tremors. Although the timing of individual events is uncertain, the overall distribution of sizes remains strikingly regular. This predictability in statistics, known as a power law, is one of the clearest signs that the Earth's behavior, though complex, follows recognizable patterns. Another key principle is the elastic rebound theory. It explains how energy accumulates and is released along faults. As tectonic plates move, stress builds up until the rocks bend and store elastic strain. When the stress exceeds the strength of the fault, the rocks snap back to their original shape, releasing energy as seismic waves. This simple mechanism applies from the smallest local tremors to the largest plate boundary earthquakes. The consistency of this process across scales shows that the Earth's crust behaves according to universal physical rules. Researchers have also found patterns in space and time. Earthquakes tend to cluster along well-defined zones, plate boundaries, subduction trenches, and mid-ocean ridges, because these are the places where stress is concentrated. Within those regions, quakes often occur in sequences. A major event is typically followed by aftershocks that decrease in frequency and strength over time, a behavior described mathematically by Amori's law. Occasionally, small earthquakes precede a larger one in the same area, forming a foreshock sequence, though not all large quakes have this warning. These patterns help scientists understand where stress is changing, even if they cannot yet predict precisely when it will be released. On a larger scale, global earthquake activity reflects the dynamic balance of the planet itself. Over millions of years, the total amount of energy released by earthquakes remains roughly steady. This long-term balance shows that the Earth is a self-regulating system. While energy builds in one region, another releases it. The crust continually adjusts to maintain equilibrium between internal heat and surface stability. Seen over geological time, the apparent chaos of earthquakes becomes a steady rhythm of energy conversion, pressure transformed into motion, motion into renewal. Mathematical models of fault systems reveal that these natural patterns resemble other complex systems found in nature. Physicists describe them as examples of self-organized criticality, a state where a system constantly evolves toward instability, releasing energy in bursts of varying sizes. This concept applies not only to earthquakes but also to avalanches, forest fires, and even financial markets. Each follows similar statistical rules. Small events are frequent, large ones are rare but inevitable. The crust of the Earth behaves like a slowly driven system that maintains balance through intermittent adjustments. Modern computer simulations allow scientists to test these ideas by reproducing the physical conditions of the crust. When stress is applied gradually to a digital model of rock, the simulated system produces small slips and occasional large ruptures, closely matching the statistical behavior observed in nature. These experiments confirm that earthquakes are not random accidents but a fundamental expression of how materials respond to long-term stress. Recognizing order in what once seemed chaos changes how we see the planet. Instead of a world ruled by sudden violence, we begin to see a vast mechanism guided by physical laws, releasing energy through structured, measurable processes. Each earthquake becomes part of a larger pattern of balance, helping the planet maintain its shape and temperature. The next time the ground moves somewhere far away, it may help to remember that the motion is not a sign of disorder, but of continuity. Beneath the surface, stress accumulates and releases according to patterns that repeat across centuries and continents. The system that seems unpredictable to us is, in reality, an intricate conversation between stability and change. A reminder that even in what feels like chaos, nature follows rules written deep within the planet's structure. Around the edge of the Pacific Ocean lies one of Earth's most active geological regions, known as the Ring of Fire. It stretches for more than 40,000 kilometers, tracing a vast horseshoe shape from the coasts of South America, up through North America, across to Asia, and down through the islands of the Pacific. Along this line, the planet's restless nature is on full display. Over 75% of all active volcanoes and roughly 90% of the world's earthquakes occur here. The Ring of Fire is not a single structure, but a connected chain of subduction zones, faults, and volcanic arcs, a continuous belt of transformation where the crust is both created and destroyed. The reason for this concentration of activity lies in the movement of the Pacific Plate, one of the largest tectonic plates on Earth. It pushes and slides against many surrounding plates, the North American, South American, Eurasian, Philippine, and Indo-Australian plates, among others. Along most of these boundaries, the denser oceanic crust of the Pacific Plate is being forced downward beneath lighter continental crust. This process, called subduction, drives both earthquakes and volcanic eruptions. As the plate descends into the mantle, it bends and fractures, releasing energy in the form of deep and powerful earthquakes. At the same time, melting rock rises through the overlying crust, feeding chains of volcanoes that stretch across continents and island arcs. Each segment of the Ring of Fire tells part of the same global story. Off the coast of South America, the Nazca Plate sinks beneath the South American Plate, creating the towering Andes Mountains and frequent large earthquakes along Chile and Peru. In North America, the subduction of the Juan de Fuca Plate has built the volcanic Cascade Range, home to peaks like Mount St. Helens and Mount Rainier. Across the Pacific, in Japan and the Philippines, complex interactions between multiple plates generate both powerful quakes and densely clustered volcanoes. Further south, near New Zealand, the boundary between the Pacific and Australian plates shifts from subduction to horizontal sliding, showing how different types of motion can coexist along a single global structure. What unites these regions is energy exchange. Subducting plates carry not only rock but also water and sediments into the mantle. The water lowers the melting point of the surrounding material, producing magma that rises toward the surface. This constant cycle of descent and ascent fuels volcanism and renews the crust. Over geological timescales, the Ring of Fire acts as one of the planet's main recycling systems, balancing the creation of new crust at mid-ocean ridges with its destruction here. Without such processes, Earth's surface would grow rigid and stagnant. The Ring of Fire also demonstrates how interconnected geological forces are. A major earthquake in one section can influence stress in another, sometimes thousands of kilometers away. While not directly triggering distant events, these adjustments subtly alter the global balance of tension within the crust. Scientists studying these patterns use satellite data and seismograph networks to track the movement of plates and estimate where energy is accumulating. Their work helps explain why certain areas remain quiet for decades and then suddenly release enormous amounts of energy in a single event. For the millions of people living along the Ring of Fire, this constant movement shapes daily life. Entire cultures have adapted to its rhythms. Buildings in Japan are designed to sway instead of crumble. Coastal communities in Chile and Alaska practice tsunami evacuation drills. Farmers in Indonesia and the Philippines benefit from fertile volcanic soils enriched by past eruptions. The same forces that bring destruction also create new land, sustain ecosystems, and drive nutrient cycles that feed the oceans. It is a vivid reminder that risk and renewal are inseparable on a living planet. The Ring of Fire is not just a region of danger but a window into the Earth's ongoing evolution. It shows how deeply the planet's interior interacts with its surface and how motion beneath the oceans shapes life above them. When we trace this glowing circle of mountains and trenches around the Pacific, we are seeing the Earth's metabolism in action, a vast, slow exchange of matter and energy that has continued for hundreds of millions of years. Every tremor, every eruption, and every new ridge along this boundary adds another line to the planet's geological record. The Ring of Fire marks not instability, but vitality, the visible edge of a world that remains active, creative, and balanced through continuous motion. Even when the surface seems completely still, the Earth never truly sleeps. Beneath the quiet of oceans and continents, the crust moves with imperceptible persistence. Every hour, thousands of small tremors ripple through the planet, too weak for us to feel but strong enough for instruments to detect. These tiny vibrations, called microseisms, are the heartbeat of the Earth's rest. They remind scientists that motion is constant, even in apparent calm. Microseisms are caused mainly by natural processes unrelated to tectonic stress. When ocean waves collide or when strong winds move across open water, They create pressure fluctuations that transfer energy into the seafloor. That energy then travels as faint seismic waves through the crust. Unlike the sharp pulses of earthquakes, these vibrations are steady and continuous, producing a global hum that fills the background of every seismogram. Even in the quietest regions, far from plate boundaries, this faint trembling never ceases. It is the sound of a planet in balance, absorbing, redistributing, and releasing energy in minute quantities. Scientists have learned much from studying these subtle signals. Because microseisms travel long distances, they can be used to monitor changes in the oceans and atmosphere. Seasonal variations in wave patterns show up as shifts in background noise levels on seismographs. Researchers can even detect distant storms or monitor melting sea ice through these vibrations. The constant movement of the Earth's surface becomes a form of environmental data, linking the solid planet with the dynamics of its oceans and air. There is another kind of low-frequency vibration known as the Earth's free oscillation. After a large earthquake, the entire planet can continue to ring like a bell for days or weeks. These oscillations are extremely slow, with periods lasting from minutes to hours, but they confirm that the Earth behaves as a single connected body. Instruments around the world record these global tremors, allowing scientists to measure the planet's density and elasticity. Every major quake, while disruptive at the surface, adds precision to our understanding of the planet's internal structure. In the last few decades, scientists have begun listening for even fainter vibrations, those generated by human activity. Traffic, industrial machinery, and construction all produce measurable seismic noise. During the global slowdown of recent years, when many cities became quiet, seismographs recorded a noticeable drop in background vibration. The change provided a rare glimpse of how deeply intertwined human life is with the planet's constant motion. Even our smallest movements become part of the Earth's vibration field. When seismologists filter out this continuous hum, they are left with the clear signatures of earthquakes. Yet that background noise itself holds beauty. It shows that stillness is never absolute and that calm is often filled with invisible motion. This idea mirrors the rhythm of rest in living beings. A person asleep is not motionless. The heart continues to beat, the lungs expand and contract, and the brain moves through cycles of activity and renewal. The planet, too, maintains a quiet pulse beneath its surface, steady, unhurried, and enduring. As you lie still, listening to the soft rhythm of your own breath, it can be comforting to imagine that the Earth is breathing with you. Its slow vibrations pass unnoticed under cities, forests, and seas, forming a lullaby made of physics and motion. Each tiny tremor helps maintain balance, just as each heartbeat maintains life. The planet's rest is not a pause but a continuous exchange of energy, as gentle and necessary as your own breathing. Sleep, like seismic quiet, is a form of restoration. It does not erase movement, it reorganizes it. In those silent hours, the body restores its balance, and the planet does the same beneath us. The next time you feel the stillness of night, remember that beneath that silence, both you and the world are quietly moving toward equilibrium, one resting body within another, each finding calm in motion. The landscapes we think of as timeless, the ridges, peaks, and high plateaus, exist because of motion deep below. Mountains are not fixed monuments of stone. They are the visible outcome of tectonic activity that lifts, folds, and compresses the crust over immense timescales. Every range on Earth, from the Andes to the Alps, owes its origin to the slow collision of plates and the forces that earthquakes occasionally reveal. Mountains form primarily through orogeny, the process of crustal deformation caused by compression. When two plates converge, one may be forced beneath the other, or both may crumple together, thickening the crust. The pressure does not act suddenly but builds gradually, deforming rock until it bends or fractures. Over millions of years, this continuous compression pushes entire regions upward. What looks like solid, immovable rock is in fact a record of flow, rock layers folded like soft fabric under extreme pressure. There are several main types of mountains. Fold mountains, such as the Himalayas, form where two continental plates collide, forcing layers of sedimentary rock to buckle and rise. Fault block mountains, like the Sierra Nevada, appear when large crustal sections break and tilt along faults, leaving elevated blocks separated by valleys. Volcanic mountains grow where magma rises from below, cooling into solid rock at or near the surface. Although their shapes and origins differ, all represent the crust responding to internal motion, compression, extension, or upwelling. The height of mountains results not only from uplift but also from the principle of isostasy, a balance between the weight of the crust and the buoyant forces of the mantle. When crustal material thickens, it sinks deeper into the mantle until buoyancy lifts it again. This equilibrium keeps mountains from growing indefinitely high or collapsing completely. As erosion removes mass from the surface, the crust rises slightly to compensate, maintaining long-term stability. Even as wind and water wear peaks down, deep processes quietly rebuild them from below. Mountains are still rising today. Satellite measurements show that many ranges continue to gain height by a few millimeters each year. Earthquakes are one sign of this motion. When faults within or beneath a mountain range slip, the land can move vertically by meters in an instant, adjusting to deeper forces at work. These sudden movements, though dramatic, are simply the quick punctuation marks in a story written mostly in slow, steady uplift. The creation of mountains has far-reaching effects on climate and life. As land rises, it alters atmospheric circulation and rainfall patterns. High elevations capture moisture, feeding rivers and glaciers that carve valleys and shape ecosystems downstream. The erosion of mountains delivers minerals to oceans, influencing biological productivity. In this way, tectonic motion connects geology with biology, linking the structure of the planet to the conditions that sustain life. Without mountains, rainfall would be less evenly distributed, and the diversity of habitats far smaller. The relationship between earthquakes and mountains is often misunderstood. Earthquakes do not build mountains directly, they are surface expressions of the deeper forces that do. Each quake represents a moment of adjustment, a small realignment within a vast system that gradually moves rock upward. Over immense spans of time, those moments accumulate, producing the relief that defines continents. What we call mountain ranges are, in essence, long-term records of energy transfer within the Earth. In studying mountain formation, scientists combine field observations with satellite imaging and computer modeling. They measure rock deformation, map fault networks, and analyze sediments carried by rivers to estimate uplift rates. These data reveal that mountain growth and erosion operate in continuous cycles. The crust thickens, the surface rises, weathering reduces the peaks, and the balance resets. An unending exchange of building and wearing down that maintains the dynamic shape of the planet. When we look at a mountain, we are seeing a process frozen at one moment in time. It appears still, but beneath it the crust moves slowly upward, while erosion carries material away. Every stone in a mountain ridge once lay deeper underground, transformed and lifted by motion. The peaks remind us that even the highest places on Earth are temporary expressions of balance. They exist because the planet refuses to rest completely, always seeking equilibrium between gravity pulling down and internal forces pushing up. While some parts of the Earth's crust rise to form mountains, others sink back into the planet's interior. This slow return of material to the mantle is known as subduction, and it is one of the key processes that keep the planet geologically alive. Without subduction, the Earth's surface would thicken and harden over time, losing its capacity to recycle material and release internal heat. Through this constant renewal, the planet maintains both its shape and its balance. Subduction occurs mainly at convergent plate boundaries, where an oceanic plate meets either another oceanic plate or a continental one. Oceanic crust, being denser and thinner, is forced downward beneath the lighter plate. As it descends, it bends and forms a deep trench on the ocean floor, the mark of a boundary where the crust begins its journey back into the mantle. The Mariana Trench in the western Pacific, nearly 11 kilometers deep, is the most striking example of this process, but similar features encircle much of the planet's oceans. The descent of a plate into the mantle is not smooth. It scrapes against the opposing plate, generating enormous friction and pressure. This friction is the source of many of the world's most powerful earthquakes. The locked interface between the two plates stores strain energy for decades or centuries until it suddenly slips, releasing seismic waves that can travel across oceans. These subduction zone earthquakes are often responsible for tsunamis, as the rapid vertical movement of the seafloor displaces large volumes of water. As the sinking slab moves deeper, it carries with it sediments, water, and minerals from the ocean floor. The high temperatures and pressures within the mantle cause these materials to release fluids that lower the melting point of the surrounding rock. This partial melting produces magma, which then rises toward the surface to form chains of volcanoes known as volcanic arcs. Examples include the Andes in South America and the island arcs of Japan and the Philippines. In this way, subduction zones link destruction and creation. The recycling of old crust fuels the birth of new land. The geological cycle of subduction influences more than just the shape of the Earth. It plays a central role in the planet's carbon cycle, regulating long-term climate stability. Carbon trapped in oceanic crust is drawn into the mantle at subduction zones, while volcanic eruptions return carbon dioxide to the atmosphere. This exchange acts as a natural thermostat, preventing the planet from freezing or overheating across geological ages. The same process that shakes the ground and raises volcanoes also contributes to the stability of conditions that allow life to persist. Deep within the mantle, the subducted plate continues its descent, sometimes reaching depths of several hundred kilometers before melting completely. Seismic imaging shows that these slabs can remain intact for millions of years, folding and sinking slowly like ribbons into the hotter rock below. The movement drives mantle convection, the great circulation that powers plate motion across the globe. The Earth's interior thus behaves as a single connected system, with energy flowing from deep within to the surface and back again. Scientists study subduction zones using networks of seismometers, ocean bottom sensors, and satellite measurements. By analyzing the speed and direction of ground motion, they can map how plates interact and estimate where stress is accumulating. Despite the complexity of these systems, the same physical principles apply everywhere. Heat, density, and gravity guide the endless exchange between surface and depth. The details vary, but the pattern remains constant, a slow descent balanced by uplift elsewhere. Subduction gives the planet longevity. It allows the crust to renew itself, removes excess heat from the interior, and sustains cycles that regulate the oceans and atmosphere. Each plate that sinks into the mantle becomes part of a continuous story of transformation. The surface we live on today includes material that once lay deep below ancient seas and will someday return there again. Seen in this light, the sinking crust is not loss but continuity, a reminder that destruction and creation are inseparable in the Earth's design. The next time you imagine the stability of the ground, it is worth remembering that beneath the calm ocean floor, whole sections of crust are sliding silently downward, recycling themselves into the heart of the planet. This invisible motion sustains the living world above it, balancing heat and matter in a system that has never stopped moving. Beneath the crust, far below the deepest mines and the roots of mountains, lies the mantle, a vast layer of solid rock that slowly moves under intense heat and pressure. Though solid, it behaves over geological time like an extremely viscous fluid, flowing in cycles that carry heat from the interior toward the surface. This motion, called mantle convection, is the fundamental driver of plate tectonics. It is the pulse of the planet, steady, patient, and essential to Earth's long-term stability. The mantle extends from the base of the crust to the outer core, a depth of nearly 3,000 kilometers. It makes up about 84% of the planet's volume. Temperatures range from about 500 degrees near its upper boundary to several thousand degrees near the core. Despite these extremes, the mantle remains mostly solid because of the enormous pressures that prevent melting. Yet under those same pressures, solid rock can deform slowly, creeping at rates of only a few centimeters per year. Over millions of years, that slow flow reshapes continents, opens oceans, and fuels earthquakes and volcanoes. Mantle convection begins with heat transfer. The Earth's core, composed mainly of iron and nickel, retains heat from the planet's formation and continues to generate new heat through radioactive decay. This energy moves outward, warming the base of the mantle. Hot material expands slightly, becoming less dense, and begins to rise. As it moves upward, it cools, becomes denser, and eventually sinks again. These rising and sinking currents create enormous convection cells, slow circulations that drive the motion of tectonic plates at the surface. Where mantle material ascends, new crust forms at mid-ocean ridges. Where it descends, old crust is recycled at subduction zones. The structure of the mantle is not uniform. The upper mantle, including a partly molten layer called the asthenosphere, is more pliable and allows plates to move above it. Beneath it lies the lower mantle, denser and more rigid but still capable of flow. Between them, there are transition zones marked by changes in mineral structure caused by pressure. Seismic studies show that these layers transmit earthquake waves differently, revealing variations in temperature and composition. Scientists use this information to map the mantle's interior in 3 dimensions, much like doctors use imaging to study the human body. Heat transfer through the mantle occurs mainly by convection, but some energy also travels as conduction, moving directly through solid rock. Over billions of years, this slow leakage of heat has cooled the planet slightly, but the balance remains. The mantle acts as a regulator, preventing the core from overheating and the surface from losing its vitality. If convection were to stop, the crust would stiffen, volcanic activity would fade, and the planet would eventually become geologically dead, like the Moon or Mars. The Earth's ability to sustain motion and renewal depends entirely on this internal circulation. Evidence of mantle motion appears everywhere on the surface. Volcanic islands rise above hotspots, where narrow plumes of mantle material reach the crust. Ocean ridges trace the lines where plates move apart above upwelling zones. Even the slow drift of continents reflects deeper currents. Computer simulations of mantle flow, built from seismic and gravity data, show that the system moves in vast cycles lasting hundreds of millions of years. Each cycle rearranges continents, alters sea levels, and influences global climate by shifting the distribution of land and ocean. The mantle's flow is not chaotic but rhythmic, following the laws of physics with remarkable consistency. Its slow pulsing sets the tempo for the entire planet, driving earthquakes, shaping landscapes, and maintaining the balance between surface and interior. From a human perspective, it seems eternal. From the planet's view, it is simply motion in its most natural form. Understanding the mantle helps us grasp why the Earth remains a dynamic world while many others have gone silent. Beneath the crust, the planet's engine continues to turn, redistributing heat and sustaining the processes that make life possible. Every tremor we feel, every eruption we witness, begins as part of this deep, invisible movement. The next time you think of the solid ground beneath you, remember that it floats on a vast, slow-moving river of rock, one that has been flowing since the planet's birth. That river is the mantle's pulse, steady and ancient, ensuring that the Earth remains alive through motion, transformation, and balance. When a major earthquake ends, the ground rarely returns to stillness immediately. The crust, having released a vast amount of stress, needs time to settle into its new position. This process produces a series of smaller tremors known as aftershocks, natural adjustments that follow the main rupture. Although they are often less intense, aftershocks can continue for days, weeks, or even months, tracing the outline of the fault that slipped. They are the echoes of the Earth finding balance after sudden motion. Aftershocks occur because the stress released during the main earthquake does not vanish evenly. When a fault ruptures, it transfers pressure to nearby segments, some of which may be pushed closer to failure. As these neighboring sections adjust, they produce smaller quakes that gradually fade in frequency and size. This pattern is described by Omori's law, which states that the rate of aftershocks decreases roughly in proportion to the time since the main event. Immediately after a large earthquake, hundreds of small shocks may occur each day. Weeks later, only a few remain. The crust slowly relaxes until the local stress field reaches equilibrium again. Although the term aftershock suggests something secondary, these events are scientifically valuable. By studying their distribution and timing, researchers can map the shape of the fault that broke and estimate how stress was redistributed. Clusters of aftershocks outline the geometry of the rupture, showing where movement was greatest and where the crust remains locked. Seismologists also use aftershock data to test building safety, as it helps reveal weak points in structures already stressed by the main quake. In this way, each aftershock contributes to understanding both geology and engineering resilience. Aftershocks can still cause damage, particularly when they strike areas weakened by the initial shaking. In cities, they may bring down structures already compromised or trigger landslides in unstable terrain. For this reason, emergency response plans often include warnings about the likelihood of further tremors. Scientists can estimate probabilities using statistical models, but not exact timing. The rule is simple: the larger the main earthquake, the longer and more numerous its aftershocks. Awareness of this pattern allows communities to remain cautious while recovery begins. The energy involved in aftershocks is small compared to the main event, yet together they represent a significant release. They function as a geological cooling-off phase, a gradual dissipation of the energy stored in the crust. Just as heat lingers after a fire, seismic motion continues after the initial rupture, fading only when balance is restored. Some faults experience thousands of measurable aftershocks, though most are too faint to be felt by humans. Sensitive instruments capture them as constant, low-level vibrations that trace the healing of the crust. Scientists also distinguish foreshocks, smaller events that sometimes precede a large earthquake in the same region. Foreshocks and aftershocks are physically similar. The difference lies only in their sequence. In hindsight, a small quake may turn out to have been a foreshock once a larger event follows. This uncertainty makes prediction difficult, as there is no clear signature separating a harmless tremor from one that signals greater motion to come. Nonetheless, by monitoring changes in aftershock activity, researchers can track how stress evolves along a fault and identify areas where the crust remains sensitive. From a physical perspective, aftershocks are the Earth's way of releasing residual tension. They mark the transition from instability to calm. The main quake breaks the locked zone. The aftershocks smooth the edges and redistribute stress. When they finally subside, the crust has reached a new equilibrium, different from before, yet stable for the time being. The process may seem chaotic, but it follows consistent rules, the same ones that govern all systems seeking balance after disturbance. There is a quiet parallel between these geological adjustments and the human experience of recovery. After moments of intense stress, neither the body nor the planet returns instantly to rest. Small reactions follow, each a minor correction on the path towards stability. Just as the Earth releases its energy gradually, people also find equilibrium step by step. What appears as lingering turbulence is, in reality, a sign that balance is being restored. When the final aftershocks fade and the instruments record only the steady hum of background noise, it means the crust has settled once more. The echoes of movement have passed, leaving the surface quiet until the next buildup of tension begins. The planet's motion continues, but for now it rests, rebalanced, unbroken, and ready for the slow rhythm of time to resume. When the ground shakes during an earthquake, we usually imagine solid rock moving beneath our feet. Yet much of the surface we live on is not solid at all. Beneath buildings, roads, and fields lies soil, an uneven mixture of sand, silt, clay, and water. Under certain conditions, this mixture can temporarily lose its strength and behave like a liquid. This phenomenon, known as liquefaction, is one of the most striking ways in which earthquakes reveal the hidden complexity of the ground. Liquefaction occurs in water-saturated soils, especially those made of loose sand or fine sediment. In normal circumstances, the grains of soil are in contact with each other, and friction between them gives the ground its stability. When an earthquake shakes the soil, however, the grains try to rearrange themselves into a denser configuration. The sudden movement compresses the spaces between them, increasing the pressure of the water trapped inside. If this pore water pressure becomes high enough, it pushes the grains apart and cancels the friction that holds them together. For a few moments, the soil behaves like a thick fluid. The result can be dramatic. Buildings tilt, roads ripple, and buried objects rise to the surface as if floating in water. The process is not permanent. Once the shaking stops, the water pressure decreases and the soil particles settle again, often in a denser arrangement than before. But during those few seconds of instability, the loss of strength can cause severe damage. Entire neighborhoods built on reclaimed land or river deltas have experienced liquefaction during major earthquakes. Foundations sink unevenly, pipelines rupture, and structures designed for solid ground fail as the earth beneath them temporarily flows. Engineers call these effects ground deformation hazards, and they can extend for kilometers beyond the main fault zone. To understand and mitigate liquefaction, scientists study the mechanical properties of soils. In laboratory tests, samples are subjected to controlled vibrations that simulate earthquake shaking. Researchers measure how different grain sizes, moisture contents, and compaction levels influence the buildup of pore pressure. From these experiments, they develop empirical models that help engineers identify areas at risk. Regions with loose, saturated sediments are classified as liquefiable zones, and construction codes require special precautions there. Modern engineering techniques can greatly reduce liquefaction damage. One approach is to densify the soil before construction, using vibration, compaction, or drainage systems that lower the water content. Another is to design foundations that can tolerate limited ground movement without collapsing. Buildings supported by deep piles anchored into stable layers beneath the liquefiable zone perform far better during earthquakes. In urban planning, knowledge of subsurface conditions is now considered as important as the design of the buildings themselves. The science of geotechnical engineering translates lessons from past disasters into preventive action. Liquefaction is also a window into the dynamic nature of the ground. What we perceive as firm and solid is, on geological timescales, fluid and adaptive. The upper layers of the earth are in constant negotiation between gravity, water, and vibration. Even without earthquakes, soils settle, compact, and slowly change. An earthquake merely accelerates that adjustment, revealing the ground's true character as a system balancing solid structure with liquid behavior. Seismologists and engineers work closely to integrate soil behavior into hazard assessments. They use microzonation maps to divide cities into regions of differing risk, taking into account both the expected intensity of shaking and the properties of the local ground. These maps guide everything from building codes to emergency planning. In this way, the physics of liquefaction becomes part of the broader goal of resilience, turning knowledge of natural processes into safety for communities. At a deeper level, liquefaction illustrates a universal principle in geology. Strength and stability are relative. Under sufficient stress, even rock can flow. Under sufficient time, even the most rigid materials yield. Earthquakes do not create weakness, they expose it. By understanding how materials behave under pressure, humanity learns to live more intelligently with a restless planet. The next time you feel the solid ground beneath you, it is worth remembering that solidity is not absolute. Underneath, countless grains of sand and droplets of water form a delicate balance that holds up cities and lives. When the earth shakes, that balance may briefly blur, reminding us that strength in nature often lies not in rigidity, but in the ability to adapt and recover. After an earthquake, the ground gradually grows quiet again. The vibrations fade, and the crust settles into its new configuration. For a time, the region may experience a kind of geological stillness, an interval scientists call seismic quiescence. It is the calm that follows motion, a pause in which the earth regains its equilibrium. These quiet periods can last for months or even years before the next cycle of strain begins. They are not signs of permanent rest, but reminders that balance in nature often comes through alternation. Activity followed by calm, tension followed by release. Seismic quiescence is an observable phenomenon in many active zones. After a major event, the redistributed stress field can reduce pressure along certain faults, leaving them temporarily stable. During this time, the number of small earthquakes drops sharply. Instruments still detect the faint background hum of the planet, but the sudden jolts disappear. For seismologists, these intervals offer valuable opportunities to study the crust in its relaxed state. Measuring how long quiescence lasts and how it ends, helps researchers understand how stress accumulates and moves through the lithosphere. Even during stillness, the Earth remains active in subtle ways. Groundwater levels adjust, microscopic cracks heal or grow, and minerals along fault surfaces slowly alter their composition. These processes occur quietly, invisible to human senses but measurable through sensitive instruments. Satellite data show that regions recovering from major earthquakes often undergo slow, continuous deformation, a gradual creep as the crust and mantle redistribute strain. This gentle motion is part of the planet's natural rhythm, maintaining stability through movement too slow to feel. In this rhythm, one can find a parallel with the cycles of rest and recovery in living systems. After effort, bodies need stillness to rebuild. Muscles repair, nerves reset, and energy stores renew. The same principle governs the Earth's rest after its deep motions. The planet's pauses are not empty. They are times of reorganization. Pressure that once caused rupture becomes distributed evenly again. Heat moves through the mantle, and the crust regains its balance. What appears as silence is, in reality, the planet breathing at a slower pace. For scientists, these quiet intervals provide a baseline against which to measure future change. Instruments that monitor seismic noise, gravity, and crustal motion continue recording even when no major events occur. The data they collect during calm periods allow precise comparisons when activity resumes. This long-term observation reveals patterns that short bursts of motion alone could never show. In this way, stillness is not absence, it is information, offering context for the planet's next movement. For those listening at night, there is something reassuring about this idea. Just as the Earth rests between its tremors, you too rest between your days. The body needs pauses as much as motion. Breathing slows, heart rhythms steady, and thoughts settle into quiet order. Sleep, like seismic calm, is not the end of activity but part of a cycle that maintains balance. Beneath you, the same pattern unfolds on a planetary scale. The crust, having released its tension, now lies still, gathering strength for the next long movement of time. Understanding this connection can bring perspective. It reminds us that motion and rest are not opposites but partners. The Earth does not fear stillness, nor does it resist motion. It alternates between them in perfect measure. When you close your eyes, you are aligning with that same natural rhythm, the cycle that keeps both planet and person in harmony. Beneath the quiet of your room, the planet continues its slow rearrangement, steady and sure, shaping itself silently while you sleep. The calm between earthquakes is not permanent, but it is necessary. It allows the planet to heal, to redistribute energy, and to prepare for the next change. In that sense, rest is not a pause in life. It is part of life's motion, the steady interval that keeps everything balanced. The Earth, vast and unhurried, rests beneath you now, sharing with you the same deep calm that follows every tremor. For much of human history, earthquakes were viewed purely as forces of destruction, unpredictable events that erased cities and left little hope for protection. Yet over the past century, engineering and science have turned that perception into something different, a relationship of understanding. Modern cities built in earthquake zones are no longer rigid fortresses hoping to resist the ground's motion. Instead, they are designed to move with it, absorbing and dissipating energy rather than fighting against it. This philosophy, flexibility over stiffness, has become the foundation of earthquake-resistant design. The principle is straightforward. When the ground shakes, every structure on it experiences acceleration. The more rigid a building is, the more likely it is to crack or collapse under that stress. A flexible structure, by contrast, can sway and bend, converting violent motion into manageable deformation. Engineers achieve this through materials, geometry, and mechanical systems that allow buildings to respond dynamically to the forces beneath them. One of the most effective innovations is base isolation. In this system, the foundation of a building is separated from the ground by layers of flexible bearings, often made from rubber, steel, and lead, that act like shock absorbers. When an earthquake occurs, the ground moves while the building above remains relatively still. The isolators lengthen the period of vibration, reducing the acceleration that reaches the structure. Many hospitals, bridges, and high-rise towers in Japan, New Zealand, and the United States now use this technology. It allows critical buildings to remain functional even after strong shaking. Another key technique involves tuned mass dampers, large weights installed near the tops of tall structures. These masses are mounted on springs and move slightly out of phase with the building during an earthquake or strong wind. Their motion counteracts the sway, reducing oscillations and protecting structural integrity. Famous examples include the Taipei 101 Tower in Taiwan and several skyscrapers in Tokyo. Though invisible to most occupants, these systems give modern architecture its quiet resilience. Beyond mechanical solutions, engineers also design for flexibility through material choice and structural redundancy. Steel frames, reinforced concrete, and composite materials can bend without breaking, distributing stress through multiple pathways. Building codes in seismic regions require that structures have enough ductility, the ability to deform under load without collapsing. This ensures that if one part of a building fails, the rest can still stand. Every column, beam, and joint is tested by computer models that simulate hundreds of possible ground motions before construction begins. Urban planners extend these principles to entire cities. Roads, bridges, and pipelines are built with joints that can stretch or slide. Power and water systems are designed to shut off automatically when shaking exceeds certain thresholds, preventing secondary disasters like fires or flooding. Schools and public buildings often double as shelters, built to the highest safety standards. Over decades, lessons from each major earthquake feed back into improved designs, creating a continuous cycle of learning between the earth and those who inhabit it. Education is part of this adaptation as well. Countries such as Japan and Chile conduct regular earthquake drills, teaching citizens how to respond calmly when the ground moves. This knowledge transforms fear into preparedness. People learn to drop, cover, and hold, to stay away from windows, and to trust the buildings designed to protect them. These social practices are as vital as the engineering itself. Together, they form a culture of resilience. When viewed from above, a modern city built in a seismic zone represents more than technology. It is a form of cooperation between humanity and the planet. Engineers have accepted that the Earth will move and have chosen to move with it. The result is architecture that does not resist nature but harmonizes with it. Bridges sway, towers flex, and underground systems slide, all in rhythm with the shaking ground. The city becomes, in a sense, alive to the planet's motion. This ability to adapt is what defines resilience. Just as the Earth maintains balance through motion, human structures now do the same. The lesson is simple but profound. Survival depends not on rigidity but on flexibility, on understanding how to yield without breaking. Every building that sways safely through an earthquake is evidence that humanity can learn to live not above the planet, but with it. The modern study of earthquakes depends on listening, hearing the planet's motion with instruments rather than ears. Each tremor, whether large or small, produces a unique pattern of vibrations that travel through the ground. When recorded by sensors, these vibrations become data, and that data becomes knowledge about how the Earth behaves. Seismology has therefore become the science of listening, turning motion into meaning and chaos into structure. At the core of this listening network are seismic stations, distributed across every continent and ocean. Each station houses highly sensitive instruments, capable of detecting motions smaller than the width of a human hair. These instruments are typically installed deep underground or on stable bedrock to minimize surface noise. The signals they capture are transmitted in real time to national and international data centers, where they are analyzed, archived, and compared. The result is a global system that monitors the heartbeat of the planet continuously. When an earthquake occurs, the first signals to arrive at a seismic station are the fast-moving P waves, followed by slower S waves and surface waves. The order and timing of these arrivals allow seismologists to determine where the event originated. By triangulating data from multiple stations, computers can calculate the location and depth of the hypocenter within seconds. This process, once performed manually with rulers and paper charts, is now automated, producing rapid alerts that can save lives by providing seconds of early warning. Early warning systems are one of the most practical outcomes of this global listening effort. In regions like Japan, Mexico, and parts of the United States, networks of sensors detect the first waves of an earthquake and immediately send alerts to cities farther away. Because electronic signals travel faster than seismic waves, these systems can give people several seconds to take protective action, enough time to stop trains, shut down industrial equipment, or move to safer locations. Though brief, these moments can make the difference between safety and catastrophe. Listening to the Earth also extends far beyond detecting earthquakes. Seismic networks pick up vibrations from landslides, volcanic eruptions, explosions, meteor impacts, and even ocean waves. Scientists use this information to monitor other natural processes in real time. In volcanic regions, for example, small harmonic tremors often precede eruptions, providing early clues of rising magma. In the oceans, pressure sensors record the passage of tsunamis generated by undersea quakes. Each type of vibration carries a signature, and together they form a language that reveals the planet's internal activity. Over the decades, improvements in technology have refined this ability to hear subtle details. Modern broadband seismometers can detect a wide range of frequencies, from the rapid jolts of local quakes to the slow, deep pulses of the planet's background vibration. Combined with GPS networks that measure ground movement in millimeters, these systems provide a comprehensive picture of how the Earth shifts and flexes. The information feeds into hazard maps, engineering models, and public education programs, all part of a coordinated effort to coexist with a moving world. The global collaboration behind seismology is remarkable. Data from thousands of stations are shared freely across nations through organizations such as the International Seismological Center and the Global Seismographic Network. When a large earthquake strikes anywhere, scientists around the world receive the signals within minutes. This openness allows for immediate analysis and rapid scientific response. The planet may be divided by geography, but its motion connects every region. A tremor in one hemisphere is recorded instantly in another, uniting researchers through shared observation. Beyond its practical uses, the act of listening to the Earth carries a quiet philosophical weight. It reminds us that the ground beneath us is not silent but alive with constant motion. Even in the stillest night, instruments register faint vibrations from distant storms or the ceaseless pounding of waves. These sounds of the Earth are too low for human ears, but real nonetheless. A steady murmur of a living planet maintaining balance through motion. To listen to the Earth is to acknowledge that we are part of its rhythm. Every vibration captured by a seismometer is a reminder that we exist on a surface in perpetual conversation with its interior. Through technology and patience, we have learned to translate that conversation into understanding. A science born not of resistance to motion, but of listening to it carefully and respectfully. Some of the most far-reaching consequences of earthquakes do not happen on land but beneath the sea. When large sections of the ocean floor move suddenly, they can displace vast volumes of water, generating tsunamis, a Japanese term meaning harbor waves. These are not ordinary waves created by wind. They are long, low pulses of energy, traveling through the entire depth of the ocean. Though barely noticeable in deep water, they rise dramatically as they approach the coast, transforming into walls of moving water that can reshape entire shorelines. A tsunami begins when an undersea earthquake, volcanic eruption, or landslide shifts the seafloor vertically. In a subduction zone, one plate slides beneath another until the accumulated strain forces part of the upper plate to spring upward. This sudden uplift pushes the overlying water upward as well, creating a broad wave that radiates outward in all directions. The initial disturbance may raise or lower the surface by only a meter, but across hundreds of kilometers, the total energy involved is immense. Because the wavelength can stretch for hundreds of kilometers, the entire ocean moves as a single mass. In deep water, tsunami waves travel at the speed of a jet aircraft, up to 800 kilometers per hour, but their height is often less than a meter, making them invisible to ships. Only when the waves approach shallower coastal waters do they slow down and grow taller. The energy that was spread through depth becomes compressed near the surface, forcing the water upward into towering surges. This transformation is what makes tsunamis so destructive. The energy of an entire ocean concentrated at the shoreline in a matter of minutes. The arrival of a tsunami is often preceded by a sudden withdrawal of water from beaches and bays. Curious observers sometimes walk onto the exposed seabed, unaware that the ocean's retreat is a warning. Minutes later, the returning surge arrives with overwhelming force. The first wave is not always the largest. Several can follow, spaced by tens of minutes, as the ocean continues to oscillate. When the waves finally subside, the coastline may be permanently changed, rivers diverted, harbors filled with debris, and landscapes redrawn by the energy of the sea. To reduce risk, scientists operate tsunami warning systems that link seismographs, ocean buoys, and satellites. When an undersea earthquake occurs, sensors measure the resulting changes in water pressure. If a significant displacement is detected, alerts are transmitted across ocean basins within minutes. These warnings give coastal communities time to evacuate to higher ground. Education is crucial too. People living near subduction zones learn to recognize natural signs, strong or prolonged shaking, the sudden retreat of water, or a deep roaring sound from the sea. Such awareness can save lives even when technology cannot respond fast enough. Tsunamis are powerful reminders of the connection between the deep earth and the surface ocean. They show that the boundaries between elements, rock and water, motion and stillness, are fluid. A movement that begins dozens of kilometers below the seabed can, within hours, cross entire oceans and reshape distant coasts. Satellite images after major events reveal the global reach of these forces. Waves reflecting, refracting, and circling the planet like ripples in an enormous pond. Despite their destructive potential, tsunamis also serve as natural tracers of ocean behavior. By studying how the waves propagate, scientists gain insights into the shape of the seafloor and the structure of ocean basins. The data collected after each event improve numerical models used for prediction and evacuation planning. In this way, even catastrophe contributes to knowledge, transforming danger into understanding. The interaction between earthquakes and tsunamis illustrates a simple but profound principle. Energy moves through systems in continuous exchange. What begins as motion in rock becomes motion in water, then motion in air and human awareness. The chain of cause and effect connects every layer of the planet. Recognizing that link encourages humility and preparedness, because it reminds us that the surface world depends on processes we cannot see. When the sea turns against the shore, it is not vengeance but physics. The same forces that create mountains and continents also drive waves that test our resilience. By studying them, and by respecting the signs they give, humanity learns to live more safely at the edge of this moving world. Every earthquake leaves a trace. Some scars are visible as fractures running across the ground, while others remain hidden deep within the rock. Over time, these marks accumulate to form the geological record, a vast, layered memory of the Earth's motion. Long after the vibrations fade, the rocks remember. They preserve evidence of stress, pressure, and heat, telling the story of a planet that has been reshaping itself since its formation. Geologists study these traces to understand both the past and the future of seismic activity. In mountain ranges, folded layers reveal ancient collisions between continents. In valleys and deserts, fault lines appear as straight ridges, offset riverbeds, or subtle steps in the landscape. Satellite imagery and aerial photography help identify these patterns across vast regions, showing how entire crustal blocks have shifted over millions of years. Every offset stream or tilted layer of sediment is a clue to how the ground once moved. Deep within the earth, fault gouge, the fine, powdered rock created when two surfaces grind against each other, acts as a record of repeated motion. By analyzing its mineral composition, scientists can estimate the temperatures and pressures involved in past earthquakes. Some faults show evidence of hundreds of ruptures, each separated by long, quiet periods. The thickness and texture of these layers reveal how often the fault has slipped and how violently. In this way, rocks function like archives, storing information about cycles of stress and release that span far longer than human memory. One of the most valuable tools in this work is paleoseismology, the study of prehistoric earthquakes. Researchers dig trenches across fault lines, examining buried sediments for signs of sudden displacement. By dating the layers above and below each disruption, they can determine when past earthquakes occurred and how large they were. This information extends our seismic history far beyond written records, sometimes covering tens of thousands of years. With it, scientists can identify long-term patterns of recurrence and estimate the probability of future events. The rocks also record more subtle processes. Microscopic studies reveal the deformation of minerals that have been twisted or stretched under stress. Some contain fluid inclusions, tiny pockets of trapped liquid that preserve the chemical conditions of their formation. When these minerals recrystallize after an earthquake, they capture a snapshot of the temperature and chemistry at that moment. Reading these details allows geologists to reconstruct the conditions deep below the surface where faults move. This geological memory reaches even further back, beyond the time of recognizable continents. The oldest rocks on Earth show signs of tectonic motion dating back billions of years. Their folded and metamorphosed structures prove that plate-like behavior began early in the planet's history. These ancient formations remind us that earthquakes are not new phenomena but expressions of the same continuous energy that has always driven the planet's evolution. In every stone lies evidence of motion, captured and preserved by time. Humanity benefits from this deep archive. By comparing modern seismic activity with records preserved in rock, scientists can test and refine models of fault behavior. They can see which regions have been active recently and which are accumulating stress. This long view provides perspective on what might seem like random events. Earthquakes that devastate a region today fit into patterns that extend far beyond our lifespans. The Earth's memory, written in stone, helps us prepare for a future that will follow the same physical rules as the past. There is something humbling about standing on an exposed fault scarp or holding a rock that once fractured miles beneath the surface. What feels solid underfoot has, at one time or another, been in motion. The ground itself is not just a foundation but a record, a chronicle of strain and renewal that continues to unfold. Each layer of rock is a page in that story, written slowly, erased partially, and rewritten again through the rhythm of geological time. Of all natural phenomena, earthquakes remain among the hardest to predict. Despite enormous advances in science and technology, no method yet exists to forecast the exact time, place, and size of an earthquake. What researchers can do is identify patterns, measure probabilities, and understand the physical processes that lead to rupture. Predicting earthquakes is therefore less about foretelling a single event and more about describing the conditions under which one is likely to occur. The difficulty lies in the nature of stress accumulation. Deep in the crust, pressure builds slowly and unevenly. Faults are complex systems, composed of rough surfaces, fluids, and minerals that respond differently to heat and strain. Even when the amount of stress can be estimated, the precise moment when a fault will slip depends on countless microscopic factors, tiny cracks, frictional changes, and shifts in pore pressure. These small variations can make the difference between quiet stability and sudden rupture. As a result, prediction in the strict sense remains beyond reach. Instead, scientists focus on probabilistic forecasting, which estimates the likelihood of an earthquake occurring in a given region over a period of years or decades. This approach relies on long-term data, maps of active faults, records of past earthquakes, and measurements of crustal movement from GPS networks. By combining these datasets, researchers can calculate how quickly strain is accumulating and how often it has been released in the past. The resulting probabilities help governments and engineers design building codes, emergency plans, and insurance systems suited to each area's risk level. Beyond statistical models, scientists also monitor a variety of precursory signals that might precede large earthquakes. These include changes in groundwater levels, gas emissions, electromagnetic disturbances, and subtle shifts in ground deformation. Some faults emit slow slip events, gradual movements that release stress without generating strong shaking. In rare cases, Swarms of small quakes or unusual patterns of seismic noise have preceded major events. However, these signals are inconsistent. Many appear without any subsequent earthquake, while some large quakes strike without warning. The challenge is separating meaningful signs from natural background variability. One of the most promising areas of research involves the use of machine learning and big data analysis. Modern seismological networks record millions of small signals each year, too many for humans to analyze individually. Algorithms trained on these vast datasets can detect subtle patterns that might escape traditional methods. Early results show that certain combinations of microseismic activity and ground deformation may indicate rising stress levels. While not predictions in the strict sense, these insights could eventually provide short-term alerts similar to weather forecasts, probabilities that increase or decrease as conditions change. Public expectation often complicates the science of forecasting. After major earthquakes, people naturally ask why they were not predicted. Scientists emphasize that the goal is not prophecy but preparedness. Because the physical mechanisms of faults are so intricate, the best defense remains anticipation and resilience. Early warning systems, strict building standards, and informed communities all arise from understanding risk rather than predicting moments. In this way, the absence of precise prediction does not mean helplessness. It means focusing on readiness. The effort to predict earthquakes has, nevertheless, deepened our understanding of the planet. Studies of crustal stress have revealed details about fluid movement, rock composition, and the structure of faults at depth. Instruments built to search for precursors have uncovered phenomena that link seismic activity with broader geophysical processes, from atmospheric pressure variations to tidal forces. Every attempt to foresee an earthquake, successful or not, adds another piece to the puzzle of how the Earth works. The desire to know when the ground will move reflects a broader human impulse, the wish to find order in uncertainty. Earthquakes remind us that even with our greatest technologies, some aspects of nature remain beyond control. Yet within that unpredictability lies a different kind of stability, the consistency of the physical laws that govern it. The planet follows rules we can study, even if we cannot schedule its motions. Our task is to learn those rules well enough to live safely within them. Earthquake prediction, in its truest form, is not about eliminating surprise, but about reducing its consequences. Through observation, education, and design, humanity turns uncertainty into manageable risk. The ground will move again, as it always has, but knowledge allows us to stand upon it with greater confidence and respect. Even in its quietest moments, the Earth never fully sleeps. The crust hums with tiny vibrations, the oceans push against the shore, and the mantle circulates in slow convection far below. From the perspective of human time, the planet's stillness seems absolute, but in geological time, there is always movement. This subtle restlessness is what keeps the Earth alive, a body that breathes slowly, cooling and shifting as it restores balance after each burst of activity. In that sense, the planet's sleep is light, never complete, and always conscious of motion. Scientists study this background activity through seismic noise, the continuous vibration of the Earth unrelated to earthquakes. Sensitive instruments reveal that the ground is never truly still. It moves by micrometers each second, driven by ocean waves, wind, and even human activity. This constant low-level motion allows researchers to study how energy flows through the crust without waiting for large quakes to occur. By analyzing changes in the character of this ambient vibration, scientists can detect subtle shifts in subsurface conditions, an increase in pore pressure, the softening of rock, or the slow deformation that may precede an earthquake. The Earth, even in rest, communicates its state. The idea of a planet that never sleeps may sound unsettling, but it offers reassurance. A static Earth would mean an Earth without renewal. The quiet movement beneath us, too small to feel but always present, circulates heat, recycles minerals, and sustains the magnetic field that shields life. It is a rhythm of gentle persistence, and one that connects every living thing to the same physical laws. Life evolved in response to this movement, adapting to a planet that flexes and breathes beneath its surface. Our sense of stability exists not in spite of that motion, but because of it. To visualize this like planetary sleep, geophysicists sometimes compare the Earth to a living organism. Its crust acts like skin, thin, flexible, and constantly renewing. The mantle beneath behaves like muscle, carrying the heat and energy that drive motion. The core, dense and molten, functions as a kind of heartbeat, generating magnetic fields that pulse outward into space. These are not poetic metaphors, but physical realities expressed in the language of science. The planet's structure and its behavior follow the same thermodynamic principles that guide living systems. Energy flows, gradients form, and equilibrium is never static. At night, when the human world grows quiet, the planet's low vibrations become easier to measure. Seismometers detect fewer signals from traffic and industry, allowing natural noise to emerge more clearly. Researchers sometimes describe these hours as the Earth's quiet window, when they can listen to the planet with minimal interference. What they hear is the deep, steady rhythm of motion, waves from distant storms, tides shifting along coasts, and faint echoes of past earthquakes still traveling through the mantle. It is a reminder that silence, in nature, is never empty. As you rest, the same principle applies. Stillness is not the absence of activity, but the presence of balance. Your heart continues to beat, your cells exchange energy, and your mind organizes experience. Beneath you, the planet performs a similar act of quiet maintenance. Heat flows outward, rocks adjust to pressure, and faults hold their tension for another day. You and the Earth are participants in the same pattern of renewal, motion contained within calm. If you find sleep arriving slowly, imagine the planet's own rhythm. Feel the faint sense that the world beneath you is breathing, its pulse deep and steady. There is no danger in that motion. It has been there since the beginning. The light sleep of the Earth is a promise of continuity, a reminder that calm and movement can exist together. The ground may tremble from time to time, but between those moments, it rests in patience, carrying all of us upon its measured, unbroken breath. The continents that define our world, Asia, Africa, the Americas, Europe, and Antarctica, are not fixed masses of land, but fragments of the Earth's crust carried by the slow drift of tectonic plates. Their movement is so gradual that, within a human lifetime, it is invisible. Yet over geological time, this steady motion has rearranged oceans, built mountains, and changed climates. The story of earthquakes is inseparable from the story of drifting continents, because both arise from the same engine of planetary motion. This concept, known as continental drift, was first supported by evidence long before the mechanism was understood. Early geologists noticed that coastlines on opposite sides of the Atlantic fit together like pieces of a puzzle, and that fossils of identical plants and animals appeared on continents now separated by vast oceans. Later, ocean floor mapping revealed symmetrical patterns of magnetic stripes on either side of mid-ocean ridges, proof that new crust was forming and spreading outward. These discoveries confirmed that continents move because the plates beneath them move, driven by convection within the mantle. Continental drift operates at a pace of a few centimeters per year, the rate at which fingernails grow. Over tens of millions of years, however, that motion becomes powerful enough to create and destroy oceans. The continents we know today are part of an ongoing cycle called the supercontinent cycle, in which land masses merge into large configurations and later break apart. Scientists have identified several ancient supercontinents, including Pangaea, Gondwana, and Rodinia, each representing a distinct phase of Earth's tectonic history. Every collision and separation produced new mountains, fault lines, and earthquake zones that still shape the world. The forces that move continents are recorded in the distribution of earthquakes across the planet. Along the boundaries where plates meet, seismic activity outlines the edges of continents with remarkable precision. The Himalayas mark the ongoing collision between India and Eurasia. The Rift Valley in East Africa shows where a new ocean may one day form. Even within stable interiors, stresses from distant boundaries can reactivate old faults, producing occasional quakes far from any visible plate edge. In this way, the motion of continents links directly to the shaking of the ground beneath our feet. Satellite technology has made it possible to measure this motion with extraordinary accuracy. Global Positioning System (GPS) receivers installed across continents record movements of just a few millimeters each year. These continuous measurements show, for example, that North America is drifting westward, Europe is moving slightly east, and Australia is heading north. The data not only confirm the theory of plate tectonics but also provide essential information for earthquake risk assessment. By tracking how strain accumulates along boundaries, scientists can estimate which regions are storing the most energy. Continental movement also influences climate, ecosystems, and evolution. As landmasses shift, they alter ocean currents and atmospheric circulation, redistributing heat and moisture across the globe. The rise of mountain ranges affects rainfall patterns and creates new habitats. Over time, these changes drive adaptation and migration, shaping the diversity of life. In this sense, earthquakes and drifting continents are not isolated geological curiosities. They are part of the same system that has guided the planet's biological history. Understanding continental motion helps explain why no place on Earth is truly permanent. The land we call home today was once underwater, and what is now ocean may one day become mountain. The ground beneath us is not a finished structure but a moving platform within a larger cycle of renewal. Even when the motion seems slow beyond comprehension, it remains steady, governed by forces deep within the planet that never rest. The slow dance of the continents continues silently, reshaping the face of the Earth with the same persistence that drives earthquakes and volcanic eruptions. Every tremor is a brief note in that larger symphony of motion. And though human civilization lasts only a moment in geological time, our instruments now allow us to witness the grand choreography unfolding beneath our feet, a dance of continents that defines the living surface of our world. Beneath some of the world's busiest cities lie quiet fractures in the rock, fault lines that extend for hundreds of kilometers, often hidden beneath layers of soil, concrete, and steel. These invisible structures connect urban life with the slow movements of the planet. Every street, bridge, and building rests on the same crust that bends, stretches, and stores energy deep below. When that energy is released, the effects can reach far beyond geology, reminding humanity that even our most advanced civilizations exist within the framework of natural motion. Faults beneath cities are not unusual. Many of the locations chosen for early settlements were also areas where the Earth's crust was already fractured. Valleys created by faulting often provide access to water, fertile soil, and natural transportation routes. River basins, deltas, and coastlines owe their shape to tectonic processes that also produce earthquakes. Over centuries, people built communities in these regions for practical reasons, rarely aware of the deep structures below. Today, satellite imaging and ground-penetrating radar reveal how intertwined human geography and geological features truly are. In places like San Francisco, Istanbul, Tokyo, and Mexico City, seismic hazards are part of daily life. Each of these cities sits near major fault systems: the San Andreas, the North Anatolian, the Sagami, and the Cocos boundaries that have shaped both their physical landscapes and their histories. Modern urban planning incorporates this knowledge, yet the challenge remains immense. Cities concentrate not only people but infrastructure, energy, and culture. An earthquake that affects an urban fault can disrupt transportation, water supplies, and communication across entire regions. Understanding how faults behave beneath cities requires a combination of geophysics, engineering, and careful observation. Seismologists map the subsurface using waves from both natural and artificial sources, constructing three-dimensional models of the crust. These models show where faults branch, where they curve, and how deep they extend. Engineers use this information to design foundations that can withstand shaking, while city planners use it to set zoning regulations and emergency response routes. The collaboration between scientists and urban designers is now a cornerstone of resilience in earthquake-prone regions. Some cities sit atop blind faults, fractures that do not reach the surface and therefore leave no visible trace. These are particularly dangerous because their presence is often unknown until they produce an earthquake. Los Angeles, for example, has several hidden faults, identified only after instrumental records revealed their motion. Ongoing monitoring using satellite radar and GPS helps detect subtle ground deformations that may indicate slow, slip, or strain accumulation along these concealed structures. The goal is not to prevent earthquakes, but to reduce their impact by anticipating where the ground might move. Construction practices have evolved dramatically to address these realities. Buildings in seismic zones are now designed to deform safely rather than resist motion outright. Bridges are built with expansion joints, allowing them to flex without breaking. Underground pipelines and tunnels include sliding connections that absorb displacement. Even critical utilities, electric grids, hospitals, communication centers, are distributed to ensure redundancy if one area is damaged. These measures transform the relationship between cities and the faults beneath them, from one of vulnerability to one of coexistence. Yet the presence of faults also gives rise to resilience in less tangible ways. Communities that live with earthquakes often develop a collective awareness of risk and preparedness. Regular drills, emergency education, and shared cultural memory strengthen social bonds. People learn to rebuild quickly, adapting their architecture and infrastructure with each generation. Over time, this awareness becomes part of a city's identity, an understanding that stability does not mean immobility but readiness to move when the earth does. Faults beneath cities symbolize the balance between human ambition and planetary reality. We build upward and outward, but the foundation remains the same shifting crust. Recognizing this connection does not diminish progress, it deepens it. It encourages designs that respect the rhythms of the planet rather than ignore them. The quiet lines running beneath our streets are not threats to be feared, but boundaries to be understood, lines that remind us that the Earth and its cities share the same heartbeat. The Earth's crust appears still, yet every moment it accumulates energy. This energy is stored in the slow bending and compression of rock, a silent process that continues over centuries. When it is finally released, the ground moves, and what seemed stable becomes a reminder of constant change. Understanding how this invisible energy builds, shifts, and transforms is central to the science of earthquakes and to our sense of the planet as a living, dynamic system. The energy of earthquakes originates in elastic strain. As tectonic plates move, they drag, collide, or slide past each other. The rocks along their boundaries deform under pressure, behaving like stretched springs. Each small increment of movement adds a little more stress. For a long time, the rocks hold this tension through their internal strength and friction, but that balance is temporary. When stress exceeds strength, the stored energy is released abruptly as seismic waves. The release may take only seconds, but it represents centuries of accumulation. Seismologists use the concept of seismic moment to measure this stored energy. It depends on three factors: the area of the fault that slipped, the average displacement during the quake, and the rigidity of the rock involved. From this calculation, they determine the moment magnitude, a measure that replaces older empirical scales. Each increase of 1 magnitude unit corresponds to roughly 30 times more energy release. A single large earthquake can unleash as much energy as thousands of smaller ones combined, yet the buildup of that energy occurs invisibly, deep within the crust. Not all stored energy becomes shaking. Some is converted into heat, some into frictional melting of rock, and some into long-term deformation that alters landscapes. In some regions, the energy release is so gradual that no earthquake occurs at all. These creeping faults move continuously at rates of millimeters per year, releasing stress through slow slip rather than sudden rupture. Studying them helps scientists understand the boundary between steady motion and abrupt failure, a key to deciphering why certain faults remain quiet while others break violently. The storage and release of seismic energy also affect the topography of the planet. When faults move repeatedly over millions of years, they uplift mountains, tilt valleys, and create basins. The quiet accumulation of strain in one area may raise land imperceptibly, preparing the ground for future earthquakes. Geodesists, using satellite-based measurements, can detect these slow deformations with astonishing precision. By comparing annual movement data, they see where the crust is flexing upward or downward, indicating where potential energy is increasing. The Earth's landscape, in this sense, is an ongoing record of its internal mechanics. Energy storage in the crust is not uniform. It depends on rock type, fault geometry, and the presence of fluids within fractures. Water, gas, and molten rock can reduce friction, changing how easily a fault slips. Small variations in these factors can determine whether a fault will lock for centuries or slide quietly. Laboratory experiments using rock samples under high pressure replicate these conditions, allowing researchers to observe microfractures and heat buildup in real time. These tests show that the transition from stability to rupture is not sudden but a gradual weakening, culminating in failure when resistance can no longer match stress. The silence before an earthquake is therefore not emptiness, it is tension. The crust stores energy patiently, waiting for the moment when release becomes unavoidable. In that silence lies the continuity of the planet's motion, a rhythm too slow for human senses but fundamental to Earth's equilibrium. The ground we stand on is always negotiating between motion and resistance, between accumulation and release. Recognizing this quiet power changes our perception of stability. The absence of shaking is not the absence of activity, it is the unseen part of a cycle that makes shaking possible. Every calm year along a fault is part of a process leading toward balance. The stillness beneath our feet holds the memory of movement and the promise of more to come, a reminder that silence, in nature, often carries the weight of stored energy. The study of earthquakes does not end in laboratories or research centers. Its ultimate purpose is to protect lives. The bridge between science and safety is built through the careful translation of data into action, how measurements, maps, and models become building codes, evacuation plans, and public understanding. Every tremor recorded by an instrument becomes part of this continuous dialogue between researchers, engineers, and communities living on restless ground. Modern earthquake science relies on a global network of cooperation. Thousands of seismometers, GPS stations, and satellites feed real-time data to agencies that monitor seismic activity. These organizations, such as the United States Geological Survey, Japan's Meteorological Agency, and the European Mediterranean Seismological Center, analyze signals within seconds of an earthquake's occurrence. Automated algorithms estimate magnitude, depth, and location, while human analysts review the data to issue verified reports. This chain of communication, though technical, is the first link between scientific knowledge and public safety. Once an earthquake is detected, information moves rapidly through warning systems. In regions equipped with early warning networks, sensors near the epicenter detect the first, faster-moving P waves and send alerts before the slower, destructive S waves arrive. The lead time may be brief, 10 to 30 seconds, but even that can stop trains, close gas lines, and give people a moment to take cover. These systems rely on precise instrumentation and constant data exchange across national borders. Earthquakes do not respect boundaries, neither can the science that studies them. Bridging science and safety also depends on clear communication. Technical data mean little without public understanding. Educational campaigns teach people how to recognize warning signals and how to respond instinctively. In earthquake-prone countries, children learn drills from an early age: drop, cover, and hold on. Communities hold regular exercises simulating evacuations and emergency responses. These practices turn abstract knowledge into reflex, replacing fear with readiness. In this sense, communication is as vital as engineering. A message delivered on time can save as many lives as a strong building. Engineering transforms seismic understanding into physical protection. Structural engineers use data on ground motion to design buildings that can sway safely, bridges that can flex, and pipelines that can stretch without rupturing. They incorporate lessons from past earthquakes into improved standards, continually refining materials and designs. After every major event, teams of specialists study the damage, identifying which structures performed well and which failed. Their findings feed back into codes that shape future construction. Through this process, the memory of each earthquake strengthens the resilience of the next generation of buildings. Public policy provides the framework for these applications. Governments establish building codes, enforce zoning laws, and invest in infrastructure retrofitting. Urban planners use hazard maps created by geologists to guide development away from unstable ground or liquefaction-prone zones. Emergency services coordinate with scientists to plan evacuation routes and response logistics. Each of these steps represents a point where science meets decision-making, where understanding the planet's motion leads to practical measures that keep societies functioning after disaster. This cooperation extends beyond national borders. International research programs share real-time data and expertise, enabling global responses to major earthquakes and tsunamis. Satellite systems from multiple countries combine to provide the most accurate deformation maps, helping assess damage even in remote areas. In the aftermath of an event, teams of scientists often travel to affected regions to assist with monitoring and analysis. These collaborations illustrate a shared recognition. The Earth's behavior connects everyone, and safety improves when knowledge is collective. At a deeper level, the bridge between science and safety reflects the philosophy of living with the planet rather than against it. Instead of viewing earthquakes as purely destructive, scientists and engineers see them as natural expressions of the planet's energy. The goal is not to stop that energy, but to coexist with it intelligently, to understand how the Earth moves, and to design societies that can move with it. This shift in perspective has already saved countless lives, and will continue to do so as knowledge grows. In the end, safety begins with awareness. Every seismograph trace, every drill, and every revised code is part of a larger human adaptation to the rhythms of a dynamic Earth. The more we listen and learn, the better we can align our actions with the forces beneath us. The bridge between science and safety is not a static structure but an ongoing collaboration, built, tested, and strengthened by the same motion that shapes the world itself. Each major earthquake leaves behind not only destruction but also knowledge. Amid fallen buildings and fractured landscapes, scientists and engineers search for patterns, clues that reveal how structures failed, how the ground moved, and how people responded. These lessons, drawn from ruins, form one of the most valuable sources of information in seismology and disaster management. Through them, each tragedy becomes a teacher, guiding safer designs and wiser responses for the future. The first task after a large earthquake is documentation. Teams of specialists travel to the affected areas as soon as safety allows. They record ground deformation, map surface ruptures, and collect samples of soil and rock. Using drones and satellite imagery, they capture aerial views that show the extent of damage across cities and countryside. This visual record is vital because the physical evidence of fault movement can disappear quickly under reconstruction or erosion. Preserving it allows scientists to study how the rupture propagated and how it interacted with local geology. At the same time, structural engineers examine buildings and bridges to understand why some collapsed while others remained standing. Their work reveals the practical effects of theoretical models. They compare actual performance with predicted outcomes, testing whether design codes succeeded or failed. For instance, they may find that a building's resonance matched the frequency of the ground motion, amplifying the shaking and causing disproportionate damage. Lessons like these directly inform updates to building standards, ensuring that future structures can better withstand similar conditions. Sociologists and emergency planners also learn from the aftermath. They study how people reacted during the shaking, how quickly emergency services responded, and how communication systems performed. In many disasters, it is not only physical structures that fail but social networks, lines of information and support. Understanding how communities organize themselves under pressure helps shape more effective education and preparedness programs. The human response becomes as much a subject of study as the physics of the earthquake itself. The ruins of past earthquakes also serve as natural laboratories for long-term geological observation. Fault scarps, uplifted coastlines, and liquefaction zones reveal how the landscape changes with each event. By dating these features, scientists can reconstruct a timeline of recurring earthquakes in the same area. Archaeological evidence often adds another layer. Ancient temples, city walls, and irrigation canals, tilted or offset by prehistoric tremors, show that the ground has moved repeatedly through history. In this way, The memory of earthquakes extends far beyond modern records, embedded in both rock and culture. Modern technology enhances these lessons. Remote sensing, laser scanning, and high-resolution GPS allow researchers to measure displacements within centimeters. Computer simulations recreate how shock waves traveled through specific geological layers. These virtual reconstructions, built from post-earthquake data, reveal weak points in infrastructure and inform how future designs can redirect or absorb seismic energy. Artificial intelligence now assists in identifying patterns across thousands of recorded events, accelerating the transformation of raw observation into usable knowledge. Yet the most enduring lessons often go beyond science. Earthquakes remind humanity of its dependence on cooperation and empathy. After each disaster, people from around the world arrive to offer aid, share expertise, and rebuild. The shared vulnerability to the planet's motion becomes a bridge between cultures and nations. Recovery efforts foster innovation, stronger housing, better emergency networks, and new materials that combine strength with flexibility. From ruins, communities create not only safety, but solidarity. Every collapsed wall, every shifted street, every line on a seismograph tells a story of both loss and learning. The knowledge gained from these moments shapes the next generation of cities, technologies, and policies. Nothing erases the human cost of earthquakes, but the determination to learn from them transforms tragedy into progress. Over time, the Earth moves, and humanity moves with it, adapting step by step to its restless rhythm. The ruins left by earthquakes are therefore more than reminders of fragility. They are blueprints for resilience. They show that each failure, when studied with care, becomes part of a chain of improvement that stretches through history. In learning from destruction, people discover the continuity of creation, the same pattern by which the planet renews itself after every rupture. After the last aftershock fades and the dust has settled, the planet returns to a kind of stillness, not absolute silence, but balance. The crust, having released its tension, adjusts into its new shape. Fractures heal through mineral growth, and groundwater begins to circulate again through freshly opened cracks. In these quiet phases, scientists often say the Earth is at rest, not because motion has ceased, but because forces are once again in equilibrium. It is a pause between acts in the planet's long and unending performance of change. The idea of rest in geology differs from human rest. For the Earth, stillness means stability within movement. The mantle continues to convect, plates continue to drift, and mountains continue to rise, yet the energy that drives these processes flows smoothly rather than abruptly. Instruments record this calm as a gentle baseline, a reminder that the same forces capable of destruction also sustain the planet's renewal. Without earthquakes, there would be no mountain ranges, no valleys, no dynamic surface on which life could evolve. Motion, managed and balanced, is what keeps the Earth alive. This awareness gives scientists a particular respect for quiet times. They know that every calm period is temporary, a space for study and preparation. During these intervals, sensors are calibrated, models refined, and communities reminded of safety routines. The apparent calm becomes an opportunity to strengthen resilience before the next disturbance. In this way, human rest mirrors planetary rest. Both are periods of recovery that prepare for future motion. In the human world, calm is also essential. After any upheaval, physical or emotional, stability allows repair. The same principle applies to sleep. When you lie still at night, your body processes the day's tension, restoring balance in muscles, metabolism, and mind. This nightly reset resembles the way the Earth settles after a quake, quiet on the surface, active within. Beneath the stillness, countless adjustments take place, tiny chemical reactions, subtle realignments, flows that maintain the whole system's health. As you listen now, imagine the Earth beneath you settling into its patient rhythm. The continents, the oceans, the crust and core, all in motion, yet perfectly balanced. The tremors that once shaped mountains and valleys are part of a cycle that ensures continuity. Nothing in nature stands completely still, yet everything finds its own pace of rest. To sleep well, is to align yourself with that rhythm, to accept motion as part of peace. If sleep comes slowly, there is no need to chase it. Let your breath follow the same steady tempo that guides the planet: expansion and contraction, tension and release. With each inhale, think of the crust drawing in energy. With each exhale, think of it letting go. The planet's calm is not fragile but enduring, built from the same physics that governs your own heartbeat. You are resting on a living world that has known countless storms and found balance after each one. The story of earthquakes, in the end, is a story of renewal. From pressure and fracture come new forms, new landscapes, and new knowledge. The Earth's rest after shaking is not an ending but a restoration, a quiet confirmation that equilibrium always returns. It reminds us that peace is not the absence of energy but its perfect organization. The ground beneath you tonight holds the memory of every movement that shaped it, yet it supports you without effort. In that understanding, there is comfort. The planet rests, and so can you. Its quiet strength flows upward through everything that lives upon it, steady and certain. We from Sleepy Stories wish you a good night.